So today I wanted to show you some particular examples of non-LTE radiative transfer. We'll talk a little bit about the specific formation of the helium line and the magnesium 12 micron lines. There's some interesting non-LTE effects that are quite unexpected, that actually took a long time before people realized how these lines actually form. And I'll show a little example of two-dimensional effects where horizontal radiation changes the ionization and therefore the line of an iron line intensity in the two-dimensional geometry. So I'll talk about in helium also a little bit about the Paschen-Bach effect. We mentioned it before, but we didn't explain exactly what it is. And I didn't list the last example, sorry. So just to recapitulate, when the density is high, collisions are frequent enough and population numbers are determined by the local conditions. This is when we have LTE. You've heard that before, and I'm sure you'll remember that. In this case, also the radiation field is given by the Planck function. When you go higher up and densities drop, collisions become less frequent and radiative transitions become relatively more important. They start to determine the population numbers, and also you start to lose photons to the outside world, and therefore the source function starts to be typically depressed because you don't get any photons back from the outside world. So in this case, the populations are determined by non-local conditions, namely the radiation field that comes from different places in the atmosphere. And we'll have to find the global solutions not only in space, but also in wavelength, considering many transitions that connect with the transition that in particular that we are studying. I've shown you the hydrogen term diagram, very simple. There's the Lyman series, Balmer series, etc. We've talked about a little bit the importance of Lyman alpha for level 2, but there's nothing really complicated in this electronic structure. Now, when we go to the second element in the periodic table, helium, there's an interesting aspect that gets added, because helium, of course, has 2 electrons, and these electrons can have parallel spin or anti-parallel spin. When they have anti-parallel spin, then the total spin is 0, and we have singlets, which means the multiplicity of those levels is 1. But when the spins are parallel, they add up to a spin of 1, and we have a triplet. The multiplicity is 2 times S, where S is the total spin plus 1. And the reason for that is that this spin can combine with the orbital angular momentum of the electrons. And when you have a spin of 1, you can have 3 different orientations within that total angular momentum. There is another complication here in that there is no allowed transition from the ground level, because that is a singlet state, to these triplet states. So there is no strong radiative path from excitation or de-excitation from the ground level to these triplet levels. And the helium-10-830 lines live. This is a magnification of this area where all the triplet levels are in the term diagram. And the helium-10-830 lines are these lines from the metastable lower level here, from the metastable lowest level of the triplet system to the ground level. No, sorry. This is the metastable level of the triplet system. So This is the lowest level in this system of lines. Right. So as it turns out, the only way of populating these levels significantly is by ionization from either one of these, any of these levels to ionized helium. Is any of these lines, any of these levels here, helium-2, where you lose one electron, and then recombination, and recombination is does not care whether it goes into the singlet system or in the triplet system. So, and the only way to populate significantly these levels, these levels, is by ionization, any of these levels here, including the ground level of helium-2, to the any of the triplet levels, and then radiative de-excitation. And then finally, you'll see you have enough population in these lines, in these levels, so that you can form the helium-10-830 line. This is very nicely described in a paper that Rebecca wrote a long time ago, 2008, right? So this is the spectrum coming from active region loops, whatever it is, kind of an average spectrum, and this will ionize helium, this UV and EUV radiation field. It will ionize helium to any of the states in the helium-2 system, and then recombination will equally populate the triplet and the singlet system. As a result, these helium-10-830 sensitivity, this is the opacity in the helium-10-830 line, is marked here with gray, with the gray scale, forms in a fairly narrow band height in the atmosphere, because that radiation doesn't penetrate very far. The ionization radiation that ionizes helium-1 to helium-2 and then recombines to helium-1 again does not penetrate very far, and therefore this helium line forms in a fairly thin layer in the atmosphere. That is still, of course, corrugated because the radiation field is not the same everywhere. You can also clearly see that in these full disk images. These are two images taken with the NSO Solis telescope. That is an optic telescope. This is a magnetogram in the 630 lines, and you see where there's black and white and this salt and pepper. That's where all the magnetic fields are in the photosphere. And this is a map of the equivalent width of the 10-830 line, but it's an inverse scale, brightness scale, right? So where the equivalent width is high, it is dark here. And you see that mostly this line, the opacity in the line, or the line width, the equivalent width of the line is stronger where there is a strong magnetic field. This place, here. And almost, this line is almost not present in any of the other locations. And this is because when we look at the EUV radiation field at the same time, as shown from an SDO 193 angstrom image on this side, you see that wherever there is brightness in this ultraviolet line band, there is equivalent width in the helium-10-830 line. This is how the spectrum looks, and this is on a magnified scale. So it is actually a triplet, although two of the lines are very close together. The blue one where they are together? Red. The red one is two lines. Okay, yeah. So this is two lines, this is one line. In very quiet area, this line is like 0.5% or so. It's very tiny in the solar spectrum, and as we'll see, it is actually in part photospheric there. One way you can more or less tell, in this case by circumstantial evidence, is this time slice of the helium-10 velocity. So you take the line profile and you measure its Doppler shift and you convert that into velocity along the slit. This is the arc second along the slit, and this is time in minutes. And you see that over at different locations along the slit, the character of this line is of the oscillations in this line are very different. They change from lower frequency, larger spatial scale to shorter frequency, higher period, and much more smaller spatial scales. When you all know probably that the photospheric oscillations are mostly 5 minutes and have spatial scales of 20, 30 arcsecond. And so it clearly looks like this time slice shows some chromospheric oscillations, but also definitely some photospheric oscillations, where the period is 5 minutes rather than 3 minutes, as it's typically in the chromosphere. And the spatial scale of this oscillation is more 10, 20 arcseconds rather than a few arcseconds as it is in the chromosphere. So I think this shows really that some of the light in the helium-10 line comes from the photosphere, some of it comes from the chromosphere, depending on how much irradiation you have in the ultraviolet light. This is the, as published in this paper, indeed 2008, the off-limb emission as a function of the coronal irradiation, where solid line is the 0 irradiation, and then 2, 5, and 10 are 2, 5, and 10 times the nominal irradiation. And you see that the populations strongly in the helium triplet strongly depend on this radiation field. When we look at the contribution function, David talked about a little bit what the contribution function is. It's the integrand of the formal solution, the integral in the formal solution of the radiative transfer equation, right? You see that that if you just calculate the total contribution function, where the total source function is the sum of the contributions from the line and the continuum, and the same for the optical depth, then this is the contribution function, and it's completely photospheric. There's no, in the total contribution function, there's no chromospheric contribution at all, or not one that is visible here on this color scale. But if you separate out the contribution of the line and that of the continuum, so you rewrite the contribution function in this way, and you plot the line contribution function, then you see that there is a clear part here in the chromosphere that is due to the line. And then there is some part that is the photospheric line. But in this case, as you can see, we eliminated the contribution of the continuum. We only show the contributions from the line itself. So this again reiterates that in the intensity in this helium-10 lines, you have contributions both from the photosphere and the chromosphere, and that you have to be aware of those. Now this is the when you have the nominal irradiation, and this is 10 times the irradiation, you see that the relative importance of the chromosphere becomes much larger in the case when you have 10 times the irradiation. So where you have intense ultraviolet radiation, the line becomes almost exclusively chromospheric. Yeah, so again, optical depth unity in the line core is deep in the photosphere. So optical depth unity is really a poor measure in this case of the formation height of this line. The only reason I wanted to show this. So in summary, the helium-10-830 triplet forms in a thin slab with properties that are, because this slab is fairly thin, it's a reasonable assumption that the properties of this slab are more or less constant. And this is something that Ivan will use once he starts talking about the Hazel inversions of this spectral line. The number of populations of the helium atom are not calculated self-consistently with radiative transfer in the whole atom in typical analysis. When you use a slab like that, you have the opacity, the total opacity of this slab in the line as a free parameter, as you'll see later. Yeah, so that's what I said. So the helium-10-830 is an important diagnostic for chromospheric magnetic fields. It's very Zeeman splitting and also the effect of scattering polarization are very evident. But the chromospheric opacity of the line is very dependent on the ultraviolet radiation field, and can only occur, significant opacity in the line can only occur when you have enough ionizing radiation so that the helium atoms can combine into the triplet levels. There's a clear photosphere component in the triplet, and especially outside active regions. As you saw in the plot, in the slice over the Bifrost cube, the thin approximation is really an approximation. It's certainly not an absolute, because there are certainly variations in the height because of the corrugation of the atmosphere and the amount of irradiation, and there's strong variation, or not strong, but there are definitely variations in the density numbers because of the density and irradiation variations. So let's talk a little bit about the Paschen-Bach effect. We've seen several talks now about the Zeeman effect and how it splits lines and introduces polarization. For strong fields, the assumption that we make to evaluate the Zeeman effect is no longer true. In the case of Zeeman, you assume that the energy splitting that the magnetic field induces is a small perturbation of the spin orbit LS coupling. And this is no longer the case if the Zeeman splitting is of the order of the energy differences between the different, for 1J, for the different levels for 1J. I'm sorry, for the different J's of all the same, what is it, the same LS, right? And the modified splitting of these components results from a different kind of coupling that I'll show a little bit in a few more slides. And this is called the incomplete Paschen-Bach effect. And for typical solar magnetic fields, the level structure of the helium-10-830 line is such that we have to typically account for the Paschen-Bach effect in the helium-10-830 triplet lines. This is just an illustration that reminding you that already in 1896 the Zeeman effect was discovered, and in the sun it was first observed by Hale in 1908. This is an observation from 10 years later. This is a slit crossing the sunspot, and you clearly see the Zeeman splitting in the line. This is David talked about this, but this is the way the Zeeman splitting works. We have total angular momentum, total orbital angular momentum, total spin angular momentum. They combine into a J, total angular momentum, and this J interacts with the magnetic field. When there's a magnetic field, it starts to, semi-classically, you can imagine it starts to precess. This precession introduces energy differences that are dependent on the projection of J onto the magnetic field. And you have from minus J to plus J, which is the number of, that is 2J plus 1 levels. And these all have an energy difference that is the Landé factor times this quantum number mj, the projection quantum number of the J onto the magnetic field, times the magnetic field strength. So depending on the atomic structure that you have different line splittings, right? And when you have these splittings and you apply the selection rules, then you can have these split levels combine into different multiplets that have the opposite or that have different polarization. And that's how we measure the magnetic field with the Zeeman effect. These are the splitting patterns of the different components of the triplet. So one part is a real triplet, and the other part is more complicated splitting. That one. Now, when you have a strong field, and a strong field is defined, is not a generic number. It is a number that depends on the level structure. And strong field is in this case is when the energy separations of the states within a level becomes comparable to the separation of the levels within a multiplet, then we have what is called a strong field. So typically when we have LS coupling, we have this situation where the L and S couple into a J, and J interacts with the magnetic field. And in this case, the eigenstates in the atom that result from this LS coupling, the Zeeman splitting is a small perturbations, and these LS eigenstates are still valid representations of the eigenstates in the atom. When the field is so strong that the splitting between different J levels becomes comparable to the Zeeman splitting, this is no longer the case, and we have to separately evaluate the interaction of the magnetic field with L and with S. And we have to then, and in that case, the LS eigenstates are no longer valid eigenstates of the atom, and we have to solve explicitly for the Hamiltonian in this in the atom. So more formally, this is described this way. The Hamiltonian is the unperturbed state without magnetic field plus a contribution from the magnetic field, given by the interaction of the orbital and spin angular momenta with the magnetic field. In the case of Zeeman, we have a small perturbation, and there's just a small energy difference between the eigenvalues of the eigenstates in the atom that are a result of DLS coupling. But if you have the Paschen-Bach effect is incomplete, then we have to separately evaluate the perturbations that the orbital and the angular momentum the spin angular momentum with the interaction with the magnetic field causes. And in this case, we have the incomplete Paschen-Bach effect. I'm sorry. In this case, when the magnetic is really strong, and you can separate these contributions into independent contributions, then you have the complete Paschen-Bach effect. But typically for normal magnetic fields, you have a incomplete Paschen-Bach effect where you have a mix between these two states, and then you have to solve for these interactions explicitly. So here are is a plot of the splittings of the due to the magnetic field. This is the field strength in Gauss, and these are the energy levels of these two states. And when you apply the magnetic field, you see that these levels cross, and this is when you have to account for the Paschen-Bach effect. As long as the splittings due to the magnetic field are smaller than this energy difference, you can assume Zeeman effect. But if you once these energy levels cross, you will have to account for the Paschen-Bach effect. Now this has implications for the diagnostics. If you assume that the lines are split simply by the Zeeman effect, while the field is strong enough that the Paschen-Bach effect becomes important, you can make an error in the field that you determine, obviously. So these are the curves are the polarization PQU and the intensity of a calculation where a 500 Gauss field is applied at 50 degrees, and one case where the Paschen-Bach effect is assumed, and one case where the Zeeman effect is assumed. And so you see that there's significant difference in Stokes V and also in U. And honestly, I don't remember which one is which. Sorry. And so now, when you analyze a observation and you assume either, so you can do like a forward calculation. You can take a simulation. You can do a forward calculation with the polarization, assuming the full Paschen-Bach effect, and then you can analyze the data either assuming Paschen-Bach effect is active, or you can assume that the polarization is only due to the Zeeman effect. And if you do assume only that the Zeeman effect is present, then you make a strong underestimate of the actual magnetic field, because the Zeeman effect has a bigger polarization, and so you would underestimate the magnetic field. So in conclusion, helium-1030 spectropolarimetry needs to account for the Paschen-Bach effect. Under typical conditions, neglecting this effect will underestimate the magnetic field strength and induce spurious velocity signals, because the Paschen-Bach, the effect of the Paschen-Bach effect on the polarization profile, on the Stokes profiles, is not symmetric. You can see that here. It is because of the overlap of the lines. It strongly more, for instance, affects here. You can clearly see that this line is more affected than this line, and similarly here and here. So because of the overlap of the lines, you would introduce a spurious velocity effect. Okay, so let's switch gears a little bit. These are line profiles of magnesium 1 lines, so neutral magnesium lines at 12 micron. And 2 different lines at different positions on the disk, mu1, 0.5, and 0.2. And these are the level designations. Given what we know about how the source function affects the line profile, and given that these lines are clearly in emission, and there's a little bit of absorption and then emission, we would infer that the source function decreases, then increases again, right? And it would be maybe a reasonable assumption to assume that this source function increases because there it starts to see the chromospheric temperature. But this is actually not the case. These lines do have a source function that increases with height, but that increase is not due to the chromospheric temperature rise. If you do a calculation of the line formation of these lines with a radiative equilibrium atmosphere that just continuously decreases and never sees a chromospheric temperature rise, you would still get emission in the line cores of these lines. So why would these lines be interesting for us to look at? Well, obviously, as we know, the Zeeman splitting ratio, the ratio of the Zeeman splitting over the Doppler width is proportional to the Landé factor times the wavelength. And while this Landé factor for these lines is typically close to 1, the very long wavelength makes that you have a line splitting that is 5 times more sensitive than a typical visible line. And so you can imagine that you would see much more easily in these lines a splitting that is where you can just look at the splitting in I rather than have to measure the Stokes profiles and do an inversion. However, as you'll see, the line formation of this line is very distinctly non-LTE in that it doesn't follow temperature, but it follows some mechanism that also has to do with ionization. And of course, at this very long wavelength, the spatial resolution, which is proportional to the wavelength over the diameter of the telescope, is 20 times worse than that of a typical visible spectral line. So, as I told you, we can try different atmospheric models where I've plotted here just 3 different ones: the FAL3, early semi-empirical model, and that is very comparable actually to a radiative equilibrium model. These 2 models don't have a chromospheric temperature rise, and this is a sunspot model, the Mulby et al. Models. And all of these, when you calculate the magnesium 2 lines, magnesium 1, 12 micron lines, they all show emission in the line core, interestingly enough. But to do that, you need to really include many levels, and about 60 magnesium 1 levels, and some 200 or so lines to properly represent radiative transfer in these lines. So these lines are somewhere here high up in the what we call the Rydberg part of the term diagram. And what happens is, again, magnesium will ionize from neutral magnesium to singly ionized magnesium. It will recombine, and then by successive recombination, this ionization recombination drives actually a departure coefficient, departure from LTE high up in the term diagram here, because basically it's almost like the term is called photon suction. Interesting enough, which is a Rob Rutten term. So this photon losses, both photon losses in these lower lines here in the ultraviolet, drive a flow where recombination and then or ionization followed by recombination, and photon losses here makes that the departure coefficient of levels higher up in the term diagram are larger than departure coefficient of terms that are slightly lower. And when you remember the so when you remember that the line source function with some algebra can be written as a function of the ratio of this departure coefficients of the lower and the upper level, and the ratio of the source function over the Planck function depends in this way. And so when you have a lower level, an upper level that has a departure that is larger than that of the lower level, and you translate that into a radiation temperature via saying the Planck function compared to the source function, then you can show that at very long wavelengths, this dependence is very strong. So if you have a ratio that departs slightly from 1, you actually get a very strong response of the source function. And so this is the source function that increases with height, independent of whether you actually have a chromospheric temperature rise or not. It just depends on the radiation flow in this large small atom. And this is well represented by our calculation. This is a comparison of the observed and the computed line profiles of the two lines I showed you in the beginning, and you see that they match very well. So we understand this mechanism really well. These are the contribution functions of the different parts of the line, the continuum, this small absorption troughs, and then the line center. And this is the contribution function of the full width half max. And these are the associated source function of the different parts of the line. So you have the photosphere, then the line center sees this source function rise. That is really the result of the small departure of the from LTE, where the departure of the lower levels is smaller than that of the higher levels. And this is the source function of the trough. Okay, so the final topic that I want to talk about is effects of two-dimensional radiation on line formation. This is a simple case where you have an atmosphere and there's a magnetic field. And because the magnetic field adds pressure, you can imagine that you have to shift the atmosphere inside the magnetic structure down by a little bit, so that there is balance between gas pressure and gas pressure from plus magnetic field. Even if you would have exactly the same thermal structure inside this magnetic element, the gas pressure at the equal level would be lower in the magnetic element than the surrounding atmosphere, because you have a contribution from the pressure in the magnetic field. And this is a model that is a little bit more complex than this simple cartoon, but it works in the same way, in that you have a magnetic field and there is a balance between the inside and outside pressure. You shift the atmosphere in the inside a little bit, and you minimize the field line energy, and you get a structure like this with the magnetic field contours here and the inclination of the magnetic field indicated in this lower panel. Now, when you calculate the formation of the iron 525 line in non-LTE in a flux tube model atmosphere like that, and you do it, for instance, in column by column, so independently you trace vertical columns through this two-dimensional atmosphere, and you calculate what is the intensity. You see that you go back. So you make columns in this way, and the columns that intersect this very steep walls of the flux tube, they actually show they become bright because the lower density in the interior of the tube exposes these hot walls here. And when you do this calculation, of course, if the atmosphere inside and outside is the same, but just shifted, then the intensity, if you calculate column by column, is inside and outside is exactly the same. Because it's just shifted in height, but in principle, the stratification is the same. And apart from these hot walls, you don't see any difference in the line intensity. However, if you calculate the spectrum, when you take full account of the two-dimensional radiative transfer, you see that there is significant weakening in the interior of the tube of the strength of this line. So it's less dark. And the reason for that is that, again, looking at ionization, in the ionization of iron from iron 1 to iron 2, sorry, there's a typo there, depends strongly on the radiation field, but the radiation field decouples already higher in the atmosphere because the opacity in the radiation field is not so large, very similar to the Balmer continuum that we talked about yesterday. So the radiation field is more or less constant, but it is larger than the Planck function in the temperature minimum region and lower than the Planck function in these higher layers. But what matters, because the line forms in this region, what matters is that the radiation field is hotter than the Planck function locally. And this means that the radiation field will over-ionize the radiation field compared to the LTE situation. And so as a result, we will have a departure, population departure, the ratio of the population numbers compared to the population numbers under LTE of the same levels, that is larger than 1. We have ultraviolet radiation over ionization. And as a result, we see that the source function, or these are optical depth unity, and because of the ionization in this region, so you have radiation coming from the sides that actually ionizes iron, and so the formation height in 1.5D is constant through the flux tube, but in 2D you see that the formation height of this iron line goes to lower heights because more and more iron on these close to the hot walls is ionized by the ultraviolet radiation field coming from here. And therefore, the source function that is sampled by optical depth unity is larger because it is deeper, and therefore the line weakens. And you can see that here in this plot, which plots the flow of the radiation at the ionization edge of iron. And you see that close to the walls here, there's significant influx of the ultraviolet radiation that ionizes iron, and therefore reduces the population in iron 1, and therefore reduces the optical depth of iron 1, and makes you sample in the line core, sample higher source function values because the formation height decreases. That's my last slide. Questions? Yes. Yes.
If you go back to the first slide about the magnesium line.
Okay. Yes.
No, this one, the pro and con.
Huh?
The next one.
Next.
Yeah, where you have the pro and con of the
Yes,
thing.
yes.
So this line is very nice because it's got a long wavelength, it's magnetically sensitive, you can measure the strength of the field
Yeah,
and so on.
yes.
And then in the con, you say that it's really non-LTE, so we should be careful and so on. How related are these two things? I mean, do I care that the line is non-LTE if I want to measure the magnetic field?
No, you only care because well, it does. No, I guess you don't. But it does matter for the formation height.
Yes.
So
So
how
to
to
know
interpret how to
then-
interpret it as a signal coming from which height, you have to do the
Uh-huh.
radiative transfer, right?
And I guess that this was, I wanted to generalize the question. All these, most of the lines that we have to use, unfortunately, for chromospheric field and so on are non-LTE. But how much do I, again, care about this part of the line formation theory and so on
Yeah.
versus what I really want, which is the magnetic field?
Yeah, yes. I think it is kind of similar to using the Milner-Eddington effect, is that you get a value, but you don't necessarily know, and you get a value as a function of tau, you don't get a value as a function of height.
So, you can say, okay, I have this kind of field because in a sense, yeah, you can decouple the things, but then you don't know exactly where to position it in the overall solar atmospheric structure.
Yeah.
That is the point. Okay.
Yes, yes.
Yeah,
Yes.
okay. I wanted to
Yeah, yeah.
have
Yeah.
this. Okay, thank you.
Yeah, yeah.
uh, who's using the magnesium line? Are we using it?
No, they did, well, as you know, probably they did some observations with at Kitt Peak with the McMath.
That was like
But having
30
a
years ago or something?
yeah, Don Jennings in experiment funded by NASA, and then Matt Penn also worked on it a little bit. Of course, the seeing at the McMath was always pretty bad, even at these long wavelengths, and I have my doubts that this is a useful line just because the spatial resolution becomes
Right.
so poor.
Huh.
But it's always interesting to have additional information, right? So,
Okay. And
but building an instrument, I think requires like gold coatings and so at these wavelengths, and of course significant cooling and so because really you start to see the thermal infrared of your instrument
so you need a cryogenic instrument.
and so yeah. So yeah, I doubt I showed it because it is really an interesting radiative transfer effect where you have these emission lines, but they are not tied to a temperature rise. No, okay, let's have a. Oh, Rebecca disappeared. Know what's on the schedule? For break? 10 minutes break or so?
And they told us that if you've had an exposure, but you don't experience symptoms, you're okay to come into NCAR in the building and therefore the classroom, and that they just ask you to monitor for symptoms. And the moment you do have symptoms, to test. And technically, they ask you to test on day 5 after your exposure, regardless of symptomatic or asymptomatic condition. But that's after the school is ended at this point. So that's entirely up to your personal responsibility, of course. So essentially, we ask you to keep an eye out for if you're feeling symptomatic in one way or another, and we would like to get you tested. So we have a very limited amount of tests. I gave tests to the people that had an exposure yesterday, and they will be testing tomorrow and Friday. But at this point, this is all we can do. So again, I'm going to say this again. If anybody feels uncomfortable with this, you're welcome to go stay in your room and join in by Zoom. We don't expect anybody to be here if they're not feeling okay with it. But those are our guidelines, and we want to welcome people and, you know, back into the classroom as long as they are not symptomatic and don't have COVID. Okay. Thank you for your understanding. I know it's hard. And
Can you read this? Make it bigger? No, yeah, yes. Better? Yes? Yeah. Yeah, that's it. Oh, I noticed that because I put it on my, sorry for that. At the moment I can't, because it seems that the NSO drive doesn't allow people from outside NSO to, I try to change the access. Normally you can send it to everyone that has the link, but I'm using the Google Drive that are associated with our NSO account, and it looks like you can't do that here. So either if someone would be willing to take those files from NSO and put them in the general Google Drive, I think NSO people should be able to access the file. So I put a link in the Discord, and you probably can't access from there. They're small. And they're somewhat maybe not so essential, but I don't think that all the files that are there are in the distribution, the standard distribution. Or if someone could take them from the Google Drive and put them in the Dropbox, that is fine too. But then post the link on the Discord. Sorry for that. I didn't realize that the NSO drive is like that. So today I wanted to give you a brief flavor of the Python routines that are available with RH now, to read the output files and to make it easy to plot different quantities, etc. So the Python routines are, there's a Python subdirectory in the main RH distribution, and if you go in there, and you look at the files there, there's a directory RH analyze that has several Python files that contain all the functions and structures that are used. You'll have to make sure that this directory, this RH analyze directory, is visible to your Python path if you want to use that. And in the Python directory, there are also several Python notebooks, and we'll use the RH analyze Python notebook that I put on my Google Drive, but apparently the NSO Google Drive doesn't allow access by people outside of NSO. So, so can you see them, Jana? Okay, great, wonderful. Yes. So before that, let me just go to the F1D directory that you should have. And there, typically, the distribution comes with one run directory. So typically what I do, personally at least, is that inside my RHF1D, I have different run files for different cases that I want to, situations for which I want to calculate the spectra. And if I go into this run directory, then I have the input files that we talked about yesterday. And one of them, of course, is the keyword.input. And again, it's probably too small, so make it bigger.
Han and
Yeah.
everybody, I put Han's files in day 8 in the Google Drive under a directory called RH scripts. And I can share the drive with you all again. Anybody doesn't have it.
Sorry, my fonts are already small, so I don't know. Looking for a way to make it easy, to make it bigger, but obvious. Okay, well, in this case, so in the I'm sorry, this is not very visible, and I don't know how to make it bigger here. I use so this is still the same size. Doesn't help me. Guess we can do it this way. Okay, there you go. So in the you all have, if you downloaded the distribution from the GitHub, it came with a RHF1D/run directory, And if you go there, you edit the keyword.input file, you see that we're using the standard file C atmosphere, the standard abundance files. We have an atoms.input, which in this case has two active atoms, hydrogen and calcium 2. And it doesn't do much else. We do have a magnetic field, and I'm not sure if that is part of the distribution or not. I think there should be some magnetic field case, so you can see if it probably in the Atmos directory of your distribution there are some magnetic fields. No? Okay. It's not that important. So actually we can, if we just comment out magnetic field, this parameter, should be able to so typically, if you start a run, it is safer to remove the output files from a previous run. And now we should be able to run the code. And so if you don't put the comment on the first column, it will give you a problem. So in this case, we solved the radiative transfer for the Val C model with both the hydrogen and calcium in non-LTE. Has anyone been able to run that? So if you go to the run directory in your RHF1D distribution, and you edit the keyword.input, basically it should, you can comment. So I commented out the magnetic field, the .b file, and then you should be able to run the code. And if anyone manages, are you willing to share? Do you want to? Okay, I have to stop sharing, I think. So now you should be able to.
I'm a little confused. So are we using the as distributed contents of the run directory?
Yes.
But do we need to modify the?
So you have to, in this case, I modified the atoms.input file.
Okay.
And I made hydrogen and calcium to
Both
active.
active.
Yes, and the rest of the atoms are passive.
That's the only change.
That's the only change, yes. And if you are having any trouble, I mean, it's useful to mention it as well, because I'm sure people will run into similar problems once they start trying this at home. Yeah. The hydrogen, which is the first one, and the calcium 2. So you have to make it calcium2.atom, not calcium.atom, because that is a different. Yes. So is that you, Daniel? Yeah. Okay. So here you see that H6.atom is active and calcium2.atom is active. So in that case, those two are solved in non-LTE, and all the rest of the atoms is part of the background, and therefore all the population in those atoms are assumed LTE, so that you can calculate the population numbers. One thing that you have to be careful if you change any of this is that at the top you have the number of atoms that you list. So if you add another line, you have to add that, you have to change that number. That's something that you might forget. Okay, and can you show your keyword dot input? So again, it addresses the atoms dot input at the top, and you commented out the magnetic field, the bottom, yeah. Yeah, that's commented out. And you used so at the bottom there, the number of threads is the number of parallel threads that you use when in wavelength. Depending on what kind of machine you have, how many CPUs you have, you can increase that. It's very one-dimensional, is very fast, so it probably won't make much of a difference here. As Carlos mentioned, when you use this like in Desire, you want to set it to 1 or 0, which is the same effectively, because then if you use the parallel wrapper, the load is distributed by the Python wrapper, and you don't want to mess or confuse things by having multiple threads in each of your pixels. And so you got the converged, it worked. So can you show the terminal window when it runs? Oh yeah, there it is. Okay. So you see that at the bottom, at the last part, you see that the delta there, just on the way it says iteration 12, that is those are the relative changes in the population numbers, maximum of those for the two different atoms, hydrogen and calcium. And you see they're both below the specified limit, the iteration limit of 10 to the minus 2, as it is specified in keyword input. And therefore, after 12 iterations, the code stopped the iterations and considered the solution converged. You see that in this case, we have turned on acceleration. And so can you try one thing? If you go to the keyword.input and you set the NG acceleration, the order to 0. So there, so set the order is 2, right? So set it to 0. So it means that we won't have NG acceleration, and then run the code again. And so now it takes 23 iterations to get the same solution, or hopefully the same. It should be very similar. So you see that this NG acceleration doesn't costs almost nothing, but it does significantly improve the convergence speed. Yeah. So, no, but it only stops when both fall below the iteration limit. Yes. It also continues solving the one that has already converged. Yes. Because there might be overlapping transitions between the different species. So even if one is reached already iteration limit, if you change the other one, the solution of the first one might change still. Right? So you have to have both of them and keep iterating till both are below that limit. Did anyone else succeed in having a converged solution? Yes. Yes. So can you share your screen, and we can look at your keyword.input. No, but share it anyway, because then we can talk about it if you will. Yeah. Yes. Are you able to share, Nancy, or no? If you okay. Yes. Yes. Okay. Then if you can, if you're willing to share, sure. Yes. Okay. Great. Yes. Yes. Yeah. Yeah. So if you don't specify a magnetic field, it cannot calculate.
File line have to comment out the
Yeah. So if you comment out the dot B, so go down. So there's the. So if you comment out the line above that, the Stokes input, the dot B file, then you also have to comment out this that one. Yeah. Okay. So now it should work. Yeah. So there you go. Yeah. So now also, so we talked about a little bit about the angles, right? By default, we specify the number. Oh, sorry, can you stay connected? I just want to show one more thing. Can you connect again? Can you connect again? Yep. So if you show your keyword.input file again. It says number of rays there, right? And we talked about this a little bit before, that you specify the number, but the exact values of those rays are determined by the Gauss-Legendre polynomials. So typically this does not include the vertical direction. So if you would want to calculate the intensity in the vertical direction, you have to run a second code, which is solve ray, which takes the population numbers, that takes the background opacities, and does a formal solution in the direction that you request. So if you can you edit show the ray.input file in the same directory? Yes. So it has only two numbers, and only the first one is relevant, and that is the mu value at which the solution will be obtained. So if you now run, so leave this alone for the rest. And so if you now run /solve ray, yes. So run that. Okay, so it did the solution, and now do ls. See that it created a file spectrum_1.00, which contains the intensities in the direction that you specified. So now edit the ray.input file again and change 1 to 0.5. Okay, save it. And now you run solve ray again. Yeah. And now do ls again. And you see that now it has added another file spectrum_0.5, which is the intensity at mu equal 0.5. Okay, thank you for sharing. So yeah, were people able now to run it? Let me share again then. Okay. So now let's go to the two-dimensional directory. And there you can create a directory run _triplet _546 or 76, which already I have done. So you can just create that directory, create it as an empty directory. And then what you would do typically is copy this, copy the input, all the input files from a previous run directory to your current directory. So you've created an empty directory of this name, and you copied all the input files from another run directory that you should have in your distribution to here. I'm not going to do it because I already did that. And now you the files that we made available that Rebecca just copied. If we would look we again have the similar input files, but if we look at the keyword.input file in this case, we have here the atmosphere that is in those files that I made available this morning, which is a two-dimensional slice through a three-dimensional simulation cube. So it has some granulation. And it specifies the angle set in a slightly different way. In 2 and 3 dimensional, you have predefined angle sets. This is one of them. It has, I think it has 3 rays per octant. Because again, you have to properly cover all solid angles, and you cannot just specify the number of rays. We have an atoms.input file that doesn't have any active atoms in this case. All the atoms there are passive. So if you have to edit your atoms.input file to make all atoms passive. Um, and we specify a wavelength file that is also been made available. So since we don't have any active atoms, the code doesn't add any wavelength points by itself. So you have to specify a wavelength grid, and this is a wavelength grid that covers 3 lines close together at the 5476 angstrom in the spectrum. For the rest, we leave most of the things together, and then we add a Carouse input file. So you have to uncomment that line, carouse.input. And if you look at that file, it has 1 line, and this is a list that is also provided this morning that has a that has 4 spectral lines that will be treated now in LTE. So if you look at that file, so you have to put it in a place, and then of course references it in a proper way in your carouse.input file that the code can find it. And finally, we have to make sure that we uncomment this line, because the simulation snapshot didn't have any hydrogen populations. So we have to assume that hydrogen is an LTE, so that you can only provide the total hydrogen number, not the specified numbers for each level separately. And then we specify, in this case, we do uncomment the Stokes input because we do have a magnetic field. This is also a file that was provided. So you have to point to that, the .b file, which accompanies the .atmos file that was specified in the first line. And since we don't iterate any non-LTE population numbers, we have to immediately specify, in this case, the Stokes mode full Stokes, so that the code does a polarized radiative transfer solution, not just I. And I think that's all we need. So was everyone able to make those changes? So if we leave that, and let me remove all the output files from the previous one. And now we should be able to run the two-dimensional. Oh, no, again, did the same thing. So in this case, we just run an LTE solution of these lines with polarization, which even if it's only 2D takes a while. So you should get similar output if you are able to run it. Yeah, but do you want to share yours so we can see? Yeah. Then, okay, no, so then we can change it. So we. Yes, 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 yes. So, I mean, you have two choices. You can put the files that we provided this morning in the directory that you're running and then point that to them, or you can put them in the places that they are referred to and then don't have to change the paths, right? And maybe in this case, it's easier to put things into the same directory and then it's easy, but you have to change the keyword of input to point to the right files. Yes, yes, makes sense, makes sense. Yep, yes. So who was able to run and get these results? Sorry? Okay, so you want me to stop stop? I can stop sharing. And then... That's fine. I mean, then it will just run in 1D. That's fine. Except you can't use those atmospheric files. If you just use a 1D atmosphere, that would work. But yes. Okay, so if you're in the one-dimensional file, you have the Atmos file, so you would run one-dimensional. Yes. So go down further. So now edit the atoms.input file. So edit this file, the atoms.input file. Atoms.input, this one. Edit that. Edit. Yes. No. Yeah, oh, sorry, I should take my mouse off, then I'm more clear. So you edit that. So now make all the set everything to passive. Yes. Okay. So now go back to the keyword.input file. Then go down further. So you have to add the wave table. Yes, yes, and then put the proper path there. The one that you just copied over. Should be a triplet dot wave. Okay. It should be triplet underscore 5476.wave. Okay. Does anyone else want to show the result? Yeah. Okay, so it's still running. Yeah, there you go. Yeah, so we didn't set the number of iterations to 0. Otherwise, it would skip that part because there's no active atoms. We could skip that. So what it's been iterating, what is called lambda iterating the background scattering. This is what I told you. The atmospheres have some Thomson scattering of electrons and Rayleigh scattering of neutral hydrogen and helium. And so it's lambda iterating those scattering contributions. And they shouldn't make any difference for the result. No, well, you can, so yeah, you go there. So you can set the Nmax scatter to 1. On line 34. That's the 1. So that is the background scattering. And then go further down. Set the Nmax ether to 0. On line 46. Yeah. And so now if you would run, it would just do one formal solution. So you can try it again. And you also have to then run. So it takes a little bit longer because when you have magnetic field and velocities, it has to solve for all directions, which includes 6 different ways because you have to solve up and down for 3 different directions. So that's why it takes significantly longer. If we would comment out the magnetic field, it would be much faster. Then it would just calculate I. Or you can set in the keyword.input where you set the angle, you can do set vertical, and it will just calculate the vertical direction. And we can do that because in this case we have LTE. We don't have to worry about integrating radiative rates. Okay, yeah, sure. So how much more time do we have, Rebecca? Okay, so let's, if we can have like 10 or 15 more minutes, we can go through the Python notebook after the break, and it should take 10 minutes or so. Not that. Yeah. But can I take 10 minutes from you? Sorry. Yeah. Because we just want to have an LTE solution at the wavelength that we provide. We're not interested in any hydrogen lines or calcium lines. We just want the Corus lines. And so we don't need to non-LTE iterations of any of the Yeah, so we have a half an hour break. Okay. Okay. Okay, thank you. Sorry for this running long. Okay, so one simple thing that that might help you in some cases is that if you are not sure that you set the proper keywords or which keywords you need to set, you can run the code, any of the different geometric versions with the -s, and it will show you which keywords are available, which you have set explicitly, and whether what the default values are if you haven't set them. So this is sometimes useful. It also will verify that you've set the proper proper values. So one thing is that to note is that there's most of the keywords in the different geometric versions are exactly the same, but there's one specific to the one-dimensional version, that's the n raised, and then for all the other sets, you have to set explicitly what angle set you use. So there's a subtle difference there. Anyway, what I don't want to take too much of Ivan's time, but I just wanted to briefly go through the Python notebook that I made available to you. Some of the things that are in the Python notebook should work, but some of them probably you have to calculate still, and I could help you if you are interested in finishing that later today or tomorrow or on Friday. But since I have these calculations pre-done, I can just go through the notebook. So the way that you, so if you include this RH analyze in the Python directory in your Python path, it will just find the routines and load them. And then to read the data from a certain run, you would just point to the directory in which that run is. So we made the run for calcium and hydrogen, for instance, and we made a two-dimensional run. Actually, this is a one-dimensional case, very similar to what we did with the LTE lines in the triplet 5476. And then I also did a simple three-dimensional calculation where I just calculated the intensity at 500 nanometers. But since we're running out of time, that I didn't show how to do that. So you can just go through these. Okay. And it prints some properties. In this case, oh. Why? Okay, so now we did all of them. So for instance, we plot. So we read the results from the RH1D or D1, and it looks. Some of the files all have standard names, so it looks for in that directory that you specify here. It looks for the standard names in the output files, and it reads them and preloads them, and then you can plot. For instance, if you want to plot the temperature here, so it loads an Atmos structure that has a temperature as a property, and you can plot then the temperature versus height, or you can plot population numbers of different hydrogen levels. So this is level 0 is the ground level, and level 5 in this case, since we had a 6-level hydrogen atom, will be the protons, and you also have the electron densities as a property in this Atmos structure, and you can plot those against the optical depth at 500 nanometers. So that those are those two plots, and you can take some time and look at those and see what else you can plot. Then it loads the different atoms. It loads the spectrum. And for instance, we can plot, in this case, we calculated hydrogen and, oops, I didn't. It expects two ray files here, so quickly. So I didn't run solve ray in this case, and I also want to have a different angle. So I'm not sure what I'm doing wrong here. I guess it may. No. No, it works. Computer is just slow now. So in this case, we plot, so we read the spectrum in the second directory, which is the one-dimensional version of this triplet calculation. And we plot the different Stokes parameters against wavelength. And then I told you yesterday about the let's see, the collisional rates and the radiative rates, they are also read, and you can plot the different collisional rates. So for instance, here you plot the rate from 0 to 1 and 1 to 0 as a function of height. You can also plot, so yesterday we were wondering what is the collisional, the epsilon, this ratio of collisional rates over the sum of the radiative rates plus the collisional rates. And so that is plotted here for the calcium 8542 line. And you see that it starts at 1 deep in the atmosphere, but it reaches 10 to the -3. So these values that I was talking about with the two-level atom approximation, those were realistic values. Then finally, this shows the continuum intensity at 500 nanometers for the third directory. You can look at those at the I just wanted to show you that you can in a very simple way read in all these quantities, because most of the file names are standard in the output, and then plot all these quantities. It's not, I apologize, it's not very well documented. So there's maybe some exploring to do, but once you have a framework, once you have done it a few times, you can just copy and paste, and it's very easy to extract spectra, population numbers, and make these plots. So with that, I think I will stop here and let Ivan get on with his lectures. And we can, if you have any questions, please come find me and we can talk about this, and I can show you more things of this. Or send me an email if you get stuck with something, and I'd be happy to help you and reply. Okay, so I will stop sharing and leave the Zoom. You want the microphone? Yeah.
Okay, so do you hear me okay? Wonderful. Okay. Well, super happy to be here. Let's get started. What follows in the next 3 days is gonna be very simple, well, not very simple, introduction to scattering line polarization and Hanle effect, where the main point here will be for us all to understand roughly what is going on without going all the way to the formalism. Of course, there will be a lot of equations, there will be a lot of transformations, there will be a lot of complicated integrals and so on, but they are a part of that. I'm trying, trust me, I'm trying to make them as simple as possible so that we can discuss. And also, one thing that I would like us to do here is I would like us all to participate. So in a way, there will be few points during all these talks where I will ask you, okay, I'm going to shut up for 5 minutes, and you're going to sit down with your pen and paper, or your computer or something, and try to write down something and derive something and show something that we are currently discussing. Okay, so obviously, this is maybe not something that is interesting for everybody. So in case you decide to fall asleep right now, these are the main things that you should know if you forget that you should remember if you forget everything else about scattering polarization. And it basically boils down to these few points here. The first one is that the same way that we saw many days, that intensity and automatically emissivity and opacity and polarization, actually emissivity and opacity for now, are influenced by the level populations in atoms and molecules and ions. The polarization, and namely scattering polarization, is determined by the populations of the sublevels. Okay? And the scattering polarization as such, both in the continuum as well in the spectral lines, is some sort of probe of the geometry of your scattering process, and that automatically means some sort of probe of your inhomogeneities in the mode. You can immediately now agree, even if you didn't think about this, that when things are completely isotropic and homogeneous everywhere, there won't be any polarization due to scattering, right? And you maybe know about the example that is completely unrelated to the solar physics, which is polarization of the cosmic microwave radiation, which tells us something about the inhomogeneities in the early universe, right? Conceptually similar in a way to what we're going to be talking about in the atmosphere of the sun. Hanle effect is a thing that you always hear about when people talk about scattering polarization. What is Hanle effect? Well, it's some magical effect that modifies this scattering polarization in spectral lines, and thus allows us, when we observe it, to learn something about the underlying magnetic field. We will see what are the differences and similarities compared to the Zeeman effect, but the field there, typically Hanle effect is sensitive to the much weaker fields than Zeeman effect. I'm going to try and hint how we can use it and how we are already using it, and of course through our exercises in the code called Hazel 2, we will learn how to interpret some specific type of observations in order to infer magnetic fields using simultaneously Hanle and Zeeman effect. Okay. So first of all, let me convince you, in case you didn't know about it, that scattering polarization in the solar atmosphere really does exist. There are some snapshots from a famous second solar spectrum atlas of Achim Gandorfer, where what you have is in the top panel the intensity spectrum of the sun. And sun, I really mean of the sun, which means of a huge chunk of the solar surface, in this case very close to the solar limb. And in the bottom panel, we have linear polarization. And I know that during the last few days, we didn't talk too much about polarization, but I hope you remember David's lectures from the last week. And I hope that you all can notice that this specific spectral line here has a linear polarization signal that doesn't look anything like Zeeman polarization signals. Zeeman polarization signals they had these 3 peaks, 2 negative, 1 positive, or vice versa, depending on the orientation of the magnetic field. Here it's just 1 positive peak. Famous strontium 4607 line. And as you can see it in the upper part of the spectrum, it's a very regular, very inconspicuous, very modest spectral line, but we are all crazy about it. And I will split this lecture in a way that we will first go through some basics, then we will do exercises, then in the last slot, I will show you some state-of-the-art papers and publications that deal with scattering polarization, and there you will see that people are trying to model this line with a huge amount of effort. If you want something more complicated, here are the sodium D lines, also very well known for exhibiting scattering polarization. And here there is already one miraculous thing. Spectral lines, which I hope you can recognize, you synthesized them yesterday, if I remember correctly. In the intensity, they look exactly the same. Lower panel in the scattering polarization, they look completely different. right? Remember when you typed in the atomic parameters for these lines, they were very similar. There was just what was important was the lower energy, upper energy of the levels, maybe the degeneracy of the level, so that you can find your opacity and emissivity, accurately. But the main difference here between these two lines is that they have different J numbers. That is what creates this huge difference. And for the end, something really, really complicated. This is calcium 4227 line, and it really exhibits a mess of things here, and who knows what is happening here. But we see that there is, a very, very complicated, very interesting, very broad linear polarization system. All this is without any magnetic fields. What people are doing here is they find a chunk of the sun that is almost void of any magnetic field. They integrate for a while, they sum it all up and pop these linear polarization signals show up here. And they're not huge. One is 1%, less than 1%. Fun. This is, by the way, the line that exhibits the largest scattering polarization in the solar spectrum. And at the solar limb. Later, why it is so important for it to be on the solar limb. Okay, so our plan for the lecture is pretty much like this. Believe it or not, we're going to start from the continuum processes. We're going to talk about something called Rayleigh scattering, and first we're going to make a little quiz where I will ask you to answer some questions and so on. It's going to be a little bit goofy. Then we're going to formalize it a little bit through some equations. Then we're going to talk about just directly applying it to the case of two-level atom and see what are the similarities and differences. And we will see how Hanle effect acts on such kind of effect. We don't have time, and I also don't have the knowledge of the top of my head, and I'm not comfortable enough with it to present you the general theory of spectral line polarization. However, and maybe I'm not allowed to say this, I do have a folder in my Dropbox which has a lot of these, papers and documents and so on. So if you want to read and to learn more, you can ask me and I can share these things with you. You don't have to suffer through downloading all these things. I will talk about, though, how do we add radiative transfer to all these things. I will leave that for this last lecture when we talk about state-of-the-art research and so on, and we'll have the exercises in the Hazel 2 code, which fortunately pretty much relies on what we will cover here. Okay. On to learn the general theory of spectral line polarization, set some time aside, and by some time I mean a lot of time aside, and go through this book. Book covers a lot of things. It requires you to go back and relearn a lot of things from your quantum mechanics classes that you have maybe forgotten, but it really presents a general way how to solve this thing. Fortunately, the same way that it applies to the other inversion and synthesis codes that we talked about, we do now slowly start to encounter publicly available codes for managing scattering polarization and Hanle effect. So you can learn some basics and then you can go straight to modeling if you think that's your. All right. So for starters, this is just a glimpse how this theory can be very complicated to write down. Of course, today the computer codes are doing these things to you. We won't go as deep as here, but we will write some relatively complicated expressions and try to dissect them and to see. Right. Okay. But what we will start with is something infinitely times simpler. Okay, and I want you to participate here. So what I'm going to do is I'm going to put you in the position of the observer that is lying along the z-axis of propagating electromagnetic wave. And actually, this is not going to be harmonic plane wave. You're going to imagine these as wave packets. What is a wave packet? Wave packet is a harmonic plane wave that is limited in time. So technically, it's not harmonic plane wave, but like a section of harmonic wave. Okay. And the duration of this packet is going to be, for us, for our assumption here, is going to be much smaller than some typical period between multiple packets, because of course we're going to have multiples of these. And all that is going to be much shorter than our integration time, right? So what's the message here? The message is that the waves are not overlapping, right? That's the most important thing to take. And then I'm going to ask you, for all the cases that we have here, you're going to vote. You're going to say, I'm going to ask, what is, for example, Q polarization? And then you're going to point positive, negative, or 0, okay? So please don't be shy and participate. I want to see what what we think here, and we're going to go through a set of these examples just to make peace with the fact what polarization means what, and then we're going to investigate some real life stuff. Okay, I realize I forgot my phone and the watch, so Marcel, please let me know when it's 5 minutes to 12, and I'm going to stop and continue. Okay, so let's start. First, let's remind ourselves how we define the polarization. So we won't be caring about the intensity, but we will discuss what's the relationship between intensity and the specific Stokes parameters here. So for Q, we have that positive Q. Actually, the Q is the difference. I'm not going to give you any hints. The Q is the difference between amount of energy in this and this plane, and U is rotated by 45 degrees. And we won't have circular polarization here because, as we will see, scattering polarization mostly exhibits as linear polarization signals. Okay, so very simple situation here. Is Q here positive, negative, or zero? Okay, more answers. Don't look around. It's positive. That's true. It is positive in this case. Why? Well, because all our energy is basically passed on through the oscillations along Y. Right? So what would be the relationship between Stokes Q and Stokes I here? Bell says they would be equal, I think. Yes, they would be equal. So this means that, our ray is basically 100% polarized. Does it make sense? I equals Q here. U is 0, V is 0. Okay, good. What about, just for us to remind ourselves what intensity is? Intensity is some constant times the time average of the square of the electric field, which is in this case going to be proportional to the square of the amplitude here. And Q is equal to I, and you can say that I is 1. Okay. How about, oops, I already gave you the answer, but I think we can agree here that intensity is 1 and that Q is minus I, right? So be very careful here. If I draw this with the electric field pointing to the other side, Q wouldn't be negative. It still would be positive, right? Because this is only one snapshot in time. It evolves, right? What matters is in which plane it oscillates. Good. What happens here? Here, I think we agree that intensity is 1, is 0, because the same amount is oscillating in X and Y, and U is here is minus 1, because everything is oscillating in this plane. Okay, now I have to check, actually. Did I mess this up? I hope I did not. Okay. Sample is as it should be. So this case, though, here the two different colors represent two different wave packets. Okay, their amplitudes are identical to the previous case. Okay, now they're arriving in different points in time. Think about this, and let's think about what is Q, what is U. Okay, I think Q is a little bit simpler. What is Q in this case? Remember, options are positive, negative, 0. Okay, most people are voting from positive or 0. I would say it's 0, right? Because when I measure, my integration time is so long that I'm capturing both of these wave packets, right? Different colors don't refer to different wavelengths or anything like that. They're just different wave packets. So during my integration time, I'm going to capture the same amount of energy oscillating along Y and along X. Now the harder question here. For this, feel free to sketch and to, think and jolt down whatever you need. What is Stokes U? positive. Okay, let me give you a little hint. I think it's 0, and my justification is that I did like this. Main difference between this and the previous. Difference is that these components, so what I did is now I projected my electric field vectors on positive and negative direction, right? In my previous case, when they both arrived at the same time, this component here and this component here cancel. But here, they're not going to cancel because they're arriving in different moments in time. This is how I like to illustrate something called two incoherent, or actually a case of incoherent superposition, right? So here, the amount of energy along plus y and minus y is the same, right? Plus u and minus u. So what I'm going to get is I'm going to get 0 Stokes u. Okay? Make sense to everybody? Okay, good. Right. Another way to think about this is to think about it like this, right? They're completely unable to interfere, these two electromagnetic waves, right? They are not overlapping. Okay, this is a very naive way to picture this, but it works to explain you the difference between coherent and incoherent superposition. Okay, about this case here, all the different colors are the different wave packets. What is now, actually think about it a little bit, and we're gonna take a poll. So let's see, Stokes cube, positive, negative, 0. Think positive, it is positive, right? Because more energy is transported along y than along x. What about Stokes u? Roughly, of course, I didn't draw this using very pedantic tools, so roughly. People are saying negative, some people are saying 0. I would say roughly 0, right? Because we have pretty much the same amount of, if we projected them all to this one and to this one, and sum the squares of these. What am I doing here, basically? I'm adding Q, U's, and V's of individual photons because they're completely non-coherent, right? This is a very simple rule. When things are non-coherent, I add their intensities. When they're coherent, I add their electric fields, right? Okay, very good. So this is pretty much the thing, and this is what we're doing, right? We are collecting in our detectors a bunch of photons on different polarization states, and what we actually get is that if we see some polarization, it tells us something about a statistical trend of the photon distribution in our data, right? Principle to see non-zero linear polarization, our radiation has to have some preferred direction. Now we need to convince ourselves, no, we don't need, I will try to convince you that scattering events create this preferred direction in the polarization, and without any magnetic fields, without any fancy things happening, you will get polarization in scattering events. And I think you already know that, and I hinted that at the beginning when I showed you the sunglasses and some water and things like that in the sky. And actually, yeah, I wanted to do that, but I can do it on the lunch break. And if you have polarization glasses, you can do the same. Go outside in the sky, rotate your glasses, and you will see that the degree of polarization of the sky is different in different points. Okay, and what I'm going to try to convince you now is that it's the largest at 90 degrees away from the sky, from the sun. That it should be at least the largest. Okay. Very good. So this is one very simple example of the linear polarization. Okay, so what we have is we have a source, and this source is very far away. Very important for me, for you to know, for us all to notice here, is that this thing here is a way for us, typically, we show the unpolarized light this way, but it's very important to remember that this is an incoherent superposition, right? Once I show this to my undergrad students, and they just ask me, why don't all these electric fields here cancel? Right? Question, right? They don't cancel because this is just a simplified way for us to depict incoherent superposition that I did earlier with the colors and everything else. Same here, right? We are not yet going into the reasons why the polarization here is linearly polarized, but these are also incoherent. This is also incoherent superposition of the electromagnetic waves, but this time they do exhibit a preferred direction. In this case, the polarization will be 100% along whichever axis we chose this. The fact that this here is red, this here is blue has nothing to do with polarization. It's just a consequence of the Rayleigh scattering that it scales in a specific way with the valent. We're not going to be talking about that right now. So I was watching, some of you attended it, the DKIST workshop that happened some months back. And when I showed this photo here, our colleague Andre asked me a very good question. Why is only one electric field surviving here? And then I gave him some very quick mumbo jumbo explanation about, conservation of the direction or something like that. But then I said, okay, let's do this in a more proper way. Typical way for us to model these scattering events in a classical manner is to say, electromagnetic wave propagates, it encounters a charged particle. This charged particle can be a free electron, can be an electron which is bound, so it can oscillate and so on and so on. And then it makes that particle oscillate, it makes it move, right? And the plane of the motion of that particle is going to be determined by the orientation of the electric field, right? In this case, superposition of many electric fields. We're going to jump a little bit, over that. And what we're going to say is we're going to say that our incoming electric field makes our charged particle oscillate equally along X and Y, okay? So, and the charged particle is going to emit its own electric field according to classical electrodynamics and according to this formula here. Electric field is equal to some bunch of constants, acceleration of the particle minus what is n here. N is the vector describing our line of sight, right? So in this case here, it's going to be x. In this here, it's going to be y. In this, so on and so on, right? What I want you to do now, I want you to try convince yourselves and me that this specific case here, this is yet another sketch. When we have unpolarized radiation coming to the point O, so there is an electric charge that oscillates in X and Y. I want you to convince yourself that the electric field along X is only going to have one component. Pen and paper and try to do it. Not kidding. I'm going to wait a couple of minutes. I'm going to go get my phone and my water bottle. Write this A here as a combination of AXI plus AYJ, or however you like to call the orts, the coordinate vectors, and try to derive it. Important, not because I want to torture you, but because we need to get comfortable with this, because eventually we're going to use it to explain how the spectral lines emit, if you want, and eventually to kind of understand how Hanle effect works in this classical interpretation. So it gives you some time to breathe and to try and convince yourself that it really works this way. Done? Oh, and you can compare with what you did. How I did it. I said A is this. Vector X is electric field when N is equal to X, okay? When N is a long X. So N is basically equal to I, right? Then N, actually A dot N is just AX. N is I, so I get this part here. So, and what remains is something times AY times J. My electric field is pointing parallel to the Y. Same thing happens when I say that I'm looking at the polarization propagating along Y, except X and Y change them. Okay. This is one very, we're all used to this, right? We just kind of convinced ourselves that the equation does really work out. But this is very important, right? When we have 90-degree scattering in a classical way, we expect the scattered radiation to be 100% polar. And in some cases in nature, we can get close to this. You will see that in sun, we never get close to this. Scattering polarization in solar circumstances, one degree polarization is plenty. Right. So now what we want to do here is we actually want to translate these electric fields in Stokes vectors. Won't carry out this derivation. You have it in one of these papers that I linked on Discord. And the way to do that would be to say scattered electric field. Here I give it as primed quantities. Here E1 and E2 are EX or E and EY, or however you define your coordinate system. We're going to see that actually it's always defined with respect to the propagation direction. So I don't want to keep them fixed and always call them X and Y, because sometimes I will use X, Y, and Z to determine my geometrical structure of my object, right? So I'm keeping very generic names for these things. Okay? So E1 and E2 are going to depend on these, vectors describing these are like referent vectors for me to describe the linear polarization in the incoming and outgoing direction. And then I can define my IQ, also U and V. I didn't write them all here, as a combination of these complex amplitudes here of my electric fields for the incoming, which is primed, and outgoing direction. As I said, we won't carry out this derivation, but if we did, what we would get is a complicated relationship like this. Complicated only because it has a lot of terms. What it really gives us, the reason why this is a very powerful thing is that on the right, sorry, there shouldn't be equal sign here. I'm sorry, I removed it in another slide. I will fix it. So on the left, we have the outgoing Stokes vector of my scattered ray. Here I have some constants that are just taking care of that intensity drops off as square of the radius, which this actually isn't intensity, it's the radiance. Here we have my incoming ray, and here there is some matrix consisting of a bunch of terms, and the terms depend on the orientation of E1, E2, 1 prime, E2 prime. What are E1 and E2 and E1 and E2 prime, where these are the referent directions for the polarization for the incoming and outgoing direction. Okay, and how am I going to show it? This is a very easy way for us to understand what these vectors are, right? I have incoming ray coming from the top. how I'm defining its polarization. Outgoing ray coming out here. This is how I'm, describing its polarization. This is some angle that here looks like 90 degrees because it was easy to draw, but doesn't have to be. It can be 0, can be pi, can be whatever you want. Okay, good. So now, this specific case here, how am I defining them? This purple plane here is something called scattering plane. Is determined by the directions of the incoming and outgoing photon in this case, or electromagnetic wave. E1 and E1 prime are both perpendicular to that plane, okay? And E2 prime both lie in that plane, okay? So with things that I just told you, and with definitions for A, B, C, a minute, what A, B, C, and D. Some of these be zeros, should some of these be 1, -1, gals, so on and so on. Try to calculate these. Choice of orienting E1 and E2 and E1 prime and E2 prime is really good. Really, really convenient. Why it's convenient is because these are in the plane, these two are perpendicular to the plane. So 2 of these immediately go to 0. Top of that, these two are parallel, so their product is 1. And then the only thing that remains is the product between E2 prime, and that's going to be cosine theta. Okay? Very simple. Then when you plug it in this big expression from before, you get new expression for the scattering matrix. This time it's much, much simpler. Something that we can call Rayleigh scattering matrix, which describes the relationship between the polarization of the incoming electromagnetic wave and the outgoing electromagnetic wave. Look at it for a little bit. Where the zeros are, how are these things structured? Talk a little bit what this is about. Important thing is that one block here couples, as we like to call it, I and Q. Right? So outgoing I depends on incoming I prime and Q prime. Outgoing Q depends on the incoming I prime and Q prime. But U are decoupled. Not get polarization in U and polarization in V in the outgoing ray if there is none in the incoming ray. Now, some of you might be thinking, oh, this guy is, selling us something. I remember I read the paper by blah, 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 which shows that the linear polarization in U can arise because of blah, blah, blah. That's true. Here we are talking about just one incoming ray, one outgoing ray. Very soon that allowing else gives us much more complicated situation. Okay, right. So what happens for 90-degree scattering? Cosine theta is 0, right? Sine theta is 1, right? So this is going to be, and just remember there is 1/2 here in front. So basically you can imagine that this is 1/2, 1/2, 1/2, 1/2. Okay. That case, get something like this. Density is I prime half plus Q prime half. Q is 1 prime half plus Q prime half. My outgoing intensity and linear polarization are the same, which means my wave is 100% polarized, right? What time is this? 50. Okay. In principle, I'm going to move back to this slide when we are done so that you can really convince yourself that, for example, if I have specific combination of the incoming I prime and Q prime, I will get 0 for the outgoing Q and for outgoing I. What does that mean? That means that if I polarize my wave in a specific way, when it scatters in 90 degrees, nothing will go out, right? I can also do that. We are used to thinking about incoming radiation being unpolarized, but it doesn't have to be. Okay? The book that I showed you, it presents a general picture of what happens when I illuminate my atoms with any, polarization, with any angular distribution. This is good and this is nice, and this really does a good job when we have only one incoming and one outgoing ray. For example, when we are looking at the sky here in the at the Earth, and we want to figure out its polarization. Radiation is coming from the sun. Sun is very, very far away. It's almost unidirectional. It's scattering from one direction, coming to our eyes, because, as I said, the optical thickness of the Earth's atmosphere is small, even smaller here in Boulder. Everything is fine. However, what happens if I have multiple directions? Okay, so I have one wave, one photon coming here from this Z, one coming from this Z. What is them? And they are both, and I'm looking at the amount scattered along my direction here, right? Here it's tricky to talk about the photons because photon only scatters in one direction, right? Let's think about electromagnetic waves. So there is electromagnetic wave coming down this direction, coming down this direction, and part of each of these scatters toward us, right? What is the conceptual problem here that we're going to have? What's going to make our life super miserable? Come again? How did? Let's say that we know the theta. But what other thing is the problem? That I used more than one color here. Why did I do that? Louder, louder. Let's say that they are, well, it doesn't matter, right? IQUV describes incoherent superpositions anyway, so we don't care about that. This electromagnetic wave here can be incoherent superposition of many, right? It's not about that. It's about geometry. What is the problem? How do I define my IQ, U, and V? Using what? D1 and D2 and D1 prime and D2 prime. They're different here for these two planes, right? The big pain in the neck, right? Because now I can easily apply this equation, both of these things separately. But I'm not allowed to add together their IQ, U's, and V's because they're defined in different coordinate systems for the two incoming directions for the two planes. Is that okay? See what's bothering me here. Why am I now in a problem? I'm now in a problem that, okay, we will see that for incoming directions, we cannot do anything. We have to define things along their own direction. But for the outgoing directions, I have two coordinate systems that are rotated with respect to each other. All right? Okay. So now we're going to try. Now it's our time to finish. Now what we're going to try is we're going to try to find a solution for this. We will get some carry expressions that I linked in the Discord that are called spherical tensors for polarimetry, but we will see that they are extremely powerful. And they allow us to solve this problem in a very neat way and calculate scattering polarization for anything, for any geometry, for any distribution of the incoming rays. It's going to be beautiful. A little bit cumbersome with all the sines and cosines and directions, but it's going to be beautiful. But now we have lunch to gather some energy and to continue later. If you have any questions, ask me during the lunch, okay? I'm going to leave this picture here. To be on schedule so that we can all be done and relaxed by the time for dinner. So yeah, I hope the other people join us very soon. So this is the image where we left off, right? And this is what I said the problem is, kind of, that we have for multiple incident directions, right? We have a different coordinate system for each one of these, and we need to reconcile that somehow. Okay, and the reason why this is so is because it's not always like the things that we see are not always illuminated from just one direction. Actually, in the sense of the sun, what I will try to convince you on Friday is that when we see the scattered light, we see the light that came from, technically speaking, everywhere, from all the different directions, right? And today also we're going to be talking about that a little bit, and I'll ask you to sketch some things and to talk about that a little bit. And here we see why polarization is so painful and why it is very cumbersome and very conceptually hard and very analytically, tedious to do all these things. The reason is that we need to take care about the vector nature of the electric field, right? If you go back and you talk about and you think about radiative transfer equation, interference, diffraction, all that stuff, photons, all that stuff that you learned, you only talk about the energy. You only talk about the scalar quantities. You derive all diffraction and interference theory in your optics classes, assuming the electric field is a scalar, right? It's very hard deriving all these things, considering, real vector nature of the electric field. Same thing goes for the radiative transfer. All radiative transfer or stellar atmospheres theory is just derived assuming that we have this distribution of the energy, and then that energy is being transported upwards, and some things are happening, and so on and so on. We never consider the polarization, right? Because the polarization requires us to define all these angles and to talk about it. So what are we going to do now? But we're going to first take a little detour, is we're going to try to find a way. Actually, we're not going to do that. We're just going to show what the result is, what happens when we fix the outgoing coordinate system. I just want to, I want you to accept something or pay attention to one thing. We cannot literally fix a direction for the polarization of the incoming radiation field, right? The reason for that is because the polarization is always defined with respect to the propagating direction. Okay, and I cannot say this and this are my axis for defining the polarization if the incoming ray is coming from the above, right? It doesn't make sense to define these the directions if I'm propagating along y. I always need to define it relative to the propagation direction. So the meaning, the orientation in some absolute space of my q, u, and v is always going to be different, or if you want q, u, and v prime, it's always going to be different for the incoming rays, but I want to fix it for the outgoing rays so that I can add up contributions from all the different directions. Good. So first of all, I have another quiz. It's not even a quiz. It's just let's consider this situation of what could happen in the real life, and it's related to the example that we had earlier, right? This is now literally rotated and much more ugly because I drew it. Sketch of what happened earlier, right? We have a sun, we have some blob. Later in the lecture, that blob is going to become a prominence, and that blob is very, very far away from the sun. We all agree, and give me some verbal or non-verbal reactions. Do we all agree that in this case, polarization is negative, the way we defined it, and that pretty much Q is equal minus I? Is everybody cool with that? With these two statements? Observer is where the observer is. Unpolarized radiation is coming from the sun. We convinced ourselves before that this is how the polarization plane is going to be oriented. Is everybody okay with the fact that Q is negative for the observer there? Q and I, okay, everybody agrees pretty much that Q and I are in the absolute sense the same, that all of my intensity is oscillating in this horizontal plane. Okay, good. We'll make this a little bit more complicated later. But now I want to take a little detour, and I want to talk again about something that Han already kind of covered. So I will maybe run through it a little bit more, but we'll also discuss some things that I think are important in general and also in the context of this. And that is the radiative transfer in a slab approximation when we have just scattering. When all my emission, not thermal emission, is actually emission due to the scattering of some incident radiation field. This is really important because this allows us to describe all class of phenomena that show scattering polarization, for example, prominences, filaments, coronal structures, active, all these condensations about the active regions, and so on and so on. It won't really work for the things happening inside of the solar atmosphere, but we will learn some concepts that we will later be able to apply to that to kind of generalize to that. Okay. This is some basic scalar radiative transfer that you might be used to by now, right? So what I have here is I have a slab. What is a slab? It's a block of material. You can imagine it as block of some atoms that you are, considering that are absorbing and emitting. The thickness, the geometrical thickness of that slab is L, and I describe this slab by some opacity and emissivity. I'm using chi for the opacity, J for the emissivity, that vary with wavelength, and they will vary with wavelength according to some absorption or emission profile, whatever you want, right? And we will prescribe some incident intensity here, and what we want to know is we want to know this emergent intensity here. I'm using 0 as the boundary condition plus as the outgoing, right? Always keep in mind that the intensity of the radiation is a very complicated quantity. Which sense? In sense that it's more dimensional than your other physical quantities. Intensity depends on X, Y, Z, theta, phi, wavelength, and time. So it's what? A 7-dimensional quantity. Mass depends on X, Y, Z, and time, right? The kinetic description of gases, which is much more complicated than just saying in this particle, the particle has such and such velocity. Okay, so here we are kind of prescribing the directions. And along this direction, this is how the radiative transfer equation looks like. So my change of my intensity is what is absorbed plus what minus what is absorbed plus what is emitted. And if I divide both sides with the opacity, I will get my optical depth here as an independent quantity, right? And we want to find the outgoing radiation here. Let me try. Oh, no, this is right. Important quantity for us here is going to be the opacity. And I'm going to try and convince you or remind you that if we only have spectral line processes, expression for my opacity is something like this. Actually, there is an L missing here. I will add it in the slide. But this is my opacity. It depends on the population of the lower level, because these are the atoms that are doing the absorption, right? Times some constant. That constant is in this case called Einstein coefficient for absorption, minus this factor here for stimulated emission, which is, very fantastic. And it's really wild how we can describe stimulated emission as negative absorption, but I'm not going to go there today, times bunch of constants and times some wavelet function that describes how that emission or absorption in this case is distributed through the wavelength. This just basically tells me the probability of absorbing photon at the line center wavelength is larger than in the wings, right? You are familiar with that. And I can lump all these things plus the L that I didn't put there as something called tau, which is constant quantity. It doesn't depend on the wavelength times some wavelength scaling factor, right? And this is what people would call a line center optical depth. Line integrated optical depth. It would be line center if the profile was normalized to 1. Instead, its integral is normalized to 1. So this is what we call line averaged optical depth. The reason I'm talking about this so much is because when we talk about the Hazel, this is going to be one of the free parameters of our model. So it's good for us to get used to that right now. Okay, good. So the question now is, how do I find intensity? Well, I need to know the ratio of these two, which I call source function, and then I can write the solution of this differential equation here as something like this. And if we assume that this source function is constant, the integral becomes very, very easy. The source function comes in front. I just integrate e to the minus t in these limits, and I get this solution here. Wonderful equation. Can somebody derive right now what happens when tau lambda is very, very small? Write it up. What does this expression here simplify? Some people maybe already know it by heart, right? Well, e to the minus t lambda, tau lambda is going to be 1 minus tau lambda plus blah. 1 and 1 are canceled. And I'm going to have s lambda times tau lambda. Typically, this incident, let me see, maybe I already have it written somewhere. Yes, I do. I have it. Here I assume the incident radiation is 0. I assume the tau lambda is small, and I get something like this, right? Then what I'm going to do is I'm going to assume that my simulated emission is not important, just to make a simpler statement, and I get this wonderful equation here. My intensity is proportional to the source function times a bunch of things that I don't really care about right now, times, there is also L missing here, sorry about that. When I miss it in one, I don't carry it over. But the important part is that there is NL here. NL is the population of the lower level. The intensity of the radiation that we see is proportional to the number density of the atoms that are in the lower state of the transition. How do you interpret that? So the simplest way to interpret that is to say the more absorbing material there is, the more emitting material there is. But what I'm going to convince you now is that because we talk about scattering, it's going to say the more material there is to absorb, and that absorption is actually scattering, the more light I'm going to see, okay, in this approximation here, right? Okay, then let's see what we get. Then the question is then how to find this source function, right, to see what happens next. And what we need to agree right now is that technically there should be this J appearing in the source function. J is the emission. And now we need to see what kind of formalism we use to say that this emission is due to the scattering, right? It's not there because, you know, there is some thermal excitation of my atoms and then they're emitting like we had in the solar atmosphere. It's there purely because of the scattering. Right? And now there's going to be a little bit of calculations here. And the essential thing that we need to assume is like this. I first define what my emission coefficient is. Intensity emitted per unit length. Okay, that's simply the definition of the emission. Density itself, I don't know if we defined it here in this school at all. If not, this is maybe the first time that you're seeing it. Density is a magical quantity. It's energy emitted in unit solid angle, per unit wavelength, in unit time, per unit surface, right? This is why lasers have very low energies, but huge intensities, because this small energy is emitted in very narrow angle, in very narrow, you know, wavelength region from a very small surface. Okay, right. And then what I'm going to do is I'm going to say that this emitted energy is equal to the absorbed energy. Because after all, that is what spectral line scattering is the absorption of photons in the spectral line process followed immediately by the emission of photons due to the de-excitation, right? Typically, what I always ask my students is when, you know, atom absorbs a photon, what happens next? They always say, well, it de-excites and emits a photon. No, it only happens if medium is very, very dilute, like here. But in the solar atmosphere, it mostly doesn't happen. It de-excites collisional, right? But that's a different story. So for here, we're going to assume that energy absorbed in the line process is equal to the energy emitted in the line process. And what is my absorbed energy? Well, it's the integral over solid angle, wavelength, time, and this should be A. But I wrote S because I'm so used to S, I just didn't want to use it, so I used A. So A, S and A have the same thing here. So it's the integral of the intensity over the spectral line profile. Why do I have spectral line profile? Because line absorbs more at the center, times wavelength, time, and area. This should be area. Cool. So what do I do then? Then I write again this emitted as the absorbed, as this thing here, right? And what is my absorbed intensity? It's opacity times my incoming intensity. And when I do these things, and when I integrate and then take the derivative, a lot of these things are going to cancel. So what I'm going to get? I'm going to get that my emissivity here is integral over all the directions and over all the wavelengths times incoming intensity times the absorption profile times the elementary solid angle and the wavelength. The quantity that when I derive what we divide by 4 pi, it's called mean intensity. You know that, I guess. And then times the opacity and times the line profile. Only important thing that you need to care about here is this integral divided by 1 over 4 pi. The more in total intensity comes to my point that is scattering, the more scattered radiation I have, the more that thing emits. This is essentially what this says. We can go through this. Maybe I, missed some apostrophes here or mislabeled something. So don't get hung up in equations. We can go through them later. But this is what's going on. And then later, when I write it, when I divide this with opacity to get the source function, this chi times phi lambda is going to cancel. And I'm going to get that my source function is equal to this thing here. This is the thing that we casually call mean intensity, but the technical term is scattering integral. Okay, yeah, and we make difference between scattering integral and mean intensity because in principle, mean intensity shouldn't have this valent profile here. So that's why we call it scattering integral to make the difference. So source function in the spectral line, in the case of pure scattering, is identically the same as the scattering integral. And to find the scattering integral, I need to integrate intensity, incoming intensity from all the incoming angles and over the wave. So one question for you now. Imagine that this slab here is illuminated by the sun, okay? And here, sun is somewhere down, creating this cone of radiation. If I lift the blob higher, what happens with the source function? Does it decrease or increase? And this integral is technically over all angles. So I'm integrating incoming intensity coming from all angles. So I'm putting this blob higher above the sun. This cone of radiation, where the radiation is coming from, is becoming smaller and smaller. So there is less and less contribution to this integral here. So my source function is smaller and smaller. My object is fainter and fainter in principle. Right? If I bring it lower down, it becomes darker and darker. And that's why, in principle, when you look at prominences, which are just on the limb, in H alpha, where they are almost optically thick, they're almost as bright as the solar disk. You look at them in some other wavelengths where they're optically thin, then the other important factor, which is optical depth, simply makes them very, very faint or basically transparent. But we can also talk about them on some other occasion. All right? Good. Right. So this is generally true, not only for like blobs and slabs and so on. It's just that if you have pure scattering, the source function is equal to this integral, right? And if I have, and now again, I'm saying this in great detail because when we start talking about Hazel and how Hazel works, Hazel has this machinery behind. It's solving these things. It's finding these things to find the source function for the helium-1030 and other spectral lines. So, but now you also know how to do this. If I tell you there's a prominence so high above the solar disk with this optical depth, find me the intensity, you will be like, okay, I can do that. I'm going to sketch this, cone of radiation. I'm going to integrate it to get the source function. I'm going to multiply that source function with optical depth and multiply it with this valent dependent factor. I'm going to get some emission line profile. Not that hard, right? You would need some maybe atomic parameters, some estimates of these quantities, but it could work in principle. Not that hard. And we could, if we had some time here, we could code it and maybe infer something and so on and so on. We can play with this later on the whiteboard, and we can, for example, show that this J that we can show that really outgoing intensity is gonna be proportional to the number of absorbing particles and so on and so on. So now we are happy with that. We know roughly how to calculate things for the scalar case. Now we're going to go back to polarization. And the big leap that I'm going to make at some point, not right now, is that this expression here is going to be valid for polarization too. Okay. Now, I should probably remind you that Han, a few days ago, derived this very same expression for continuum processes. And the only difference there was that we didn't have this wavelength integral and this profile here. Everything else was the same. So in that case, going from the continuum scattering to line scattering literally only meant add this integral here, add this thing here, you're done. And we're going to assume that that works for polarization too. Except for that, we're going to have to take into account a few more effects that influence polarization in spectral lines, and we're going to be talking about them in great extent. We're going back to the polarization now, and I want to remind you about this, but now I want to formally write down a few things, right? I want to write my intensity as my source function for the intensity times wavelength-dependent optical depth, which is source function for intensity, times line integrated optical depth, times the absorption/emission profile, okay? Here we are only talking about the so-called complete frequency redistribution for simplicity. If you want to discuss PRD in prominences, we can. Something, and Han is there. You can also ask him all sorts of questions about PRD, right? But now we're going to be bold. We're going to anticipate what comes next, and we're going to say that outgoing Q, which is also some kind of intensity, right? It's true that we call it polarization, but the units for that are units for intensity. It expresses some sort of energy, right? I'm going to say that it's proportional to some source function for Stokes Q times the optical depth times the wavelength function, right? Or if I want to write it concisely, I can say that my vector intensity, where vector intensity is IQUV, equal to my vector source function, SISQSU-SV, times this thing here. This contradicts a little bit what David showed, right? Because David told you that polarization arises due to, actually, let me ask you. I will not go into this. We have later some time for you to see what, right? So what we are introducing here, we're introducing a source function for polarized radiation, right? And we wrote both I and Q through it, and we knew what source function for intensity was. We don't know yet what source function for Q is, nor for U. And you are already kind of feeling, I think, that Stokes V is not going to appear here, right? The reason for that is that scattering processes don't really seem to introduce circular polarization. And in common life, they don't. When we have reflection of glasses, of rivers, of various kind of things. In continuum, they don't. But actually, in spectral lines, they can. But we won't go there right now. But you can look at the book, at the Bible, and find what happens there. But I want you to be prepared for one other very important thing, which is that source function for polarized radiation is going to be angle dependent. And the only way that I can convince you of that right now is to, going back so much, but we kind of have to go there, is to show you this plot. See that more radiation is scattered forward than under 90 degrees. And that is already tipping us off that the source function for polarized radiation is going to be wavelength dependent. When we introduce these spherical tensors of radiation field, we will explicitly see how it changes. There are two factors in this, but yeah, it's one thing that makes things extremely. And actually here, you can kind of find that, right? Take all this thing on the right, derived earlier, and replace it. Imagine it as some S times tau times phi lambda, or just times tau because it's continuum. There is no wavelength dependence. You will see that this term needs to be equal to the source function. You will see that it depends on that. This is only in the case of one incoming, one outgoing direction. When we have multiple incoming directions, things are going to become more complicated. All right. Well, now you have to sketch some things. Start from this slab. Very simple. The radiation was only oscillating along this direction here. And try to sketch what happens when this slab is closer to the solar surface. What happens with the polarization? How does electric vector oscillate? What is Q? What is U? And so on and so on. Maybe 5 minutes is too long, but I think 3.5 minutes is just fine. Get the solar surface, put the blob somewhere, illuminate it with the cone to just one direction, and try to sketch how the electric field that is scattered is behaving. And to make it simpler, what I recommend you do is I recommend you make the radiation scattered toward you. We're looking at the blob. Blob is on your page. The radiation is coming from all the sides and scattering toward you. Tell me what you get. This is example. Sorry for still talking. I'm going to let you think it's true, but this is example of the superposition of many incoherent packages, right? Many incoherent packages are coming from many directions. You're curious what happens. Will we have any preferred directions, and how will they? Catch? We can try and guess when the time. Some of you already saw this. Some of you already saw this multiple times. Still, you can convince yourself that that makes sense. Almost up. So if you didn't want to sketch, share your vote. Asking about Q and U, positive, negative, or zero. Time's up. What would you say Q is? Positive or negative or zero? But U, maybe that one is easier. Okay, I'm going to show you how I sketch this and then we can discuss it, okay? Do it like this. A lot of things happening here. This is our slab. Now it's illuminated by all of these directions here, right? Here, the radiation is scattering toward us. So this is really the electric field vector that you're seeing. Radiation coming up scatters, we see the green one, right? Radiation coming from lower left, blue one. Lower right, we see black one. Then there are also some, coming from different directions and so on and so on. When I zoom, of my electric field vectors is going to be like this. It's going to be a region of this XY space where no electric field is oscillating it. Why? There is no radiation illumination. Main point here, the thing that creates the polarization, the first effect, there is a later effect later, that this cone is not full 2 pi, is less than 2 pi. The blob is a little bit above the atmosphere. Thus, these different things conspire to give us Q, which is negative because I have predominant direction. And here we can agree that it's zero, right? Because things are completely sense. You all agree? Okay, good. So when somebody tells you prominences are polarized parallel to the limb, this is what it means. You look at the prominences from here. This is the limb. This is how they are predominantly polarized, parallel to the limb. The absence of Hanle effect, of course. Okay, harder question now. We don't need text for that. Think for a little bit. I'm not going to bore you with drawing it all over again and thinking for multiple minutes. What would happen? What do you think would happen if I had more light coming from the left than from the right? What would change? Anybody have an idea? Hunch. You don't have to prove it. Get some U signal. Very well. So imagine the situation is like this. Imagine that there is more intensity coming from this direction. Then I would see more component here. Then I would get some U that is non-zero. In this case, it would probably be positive, right? Because we define U as this minus this. This is one thing that you can use to interpret all these fancy results that you see later. Presence of Stokes U, when there is no magnetic field, implies some axial anisotropy. Okay, and this is again one more complication, is that even though this slab is just a point, even though it's just basically zero dimensional, right? If the radiation field is not axially symmetric, the emergent radiation field is not going to be axially symmetric and is going to be polarized with both IQ, U, IQ, and U. Yeah. Good. Don't model these yet, at least not for prominences. We use simpler models, but it's really good illustration for what will come later. Later, I mean on Friday, when we get to what happens in the solar atmosphere. Go ahead. Come again? No, very good observation. That's true. But also because sun is so big, typically all these observations are done on very small chunks. We're almost always gonna, well, that's not really true if you use like HMI or something like that. I don't know how they use it there. But if you were to use biggest, you would, in most of the times, you would define your Q and U relatively to the closest solar limb. So in principle, if Q is negative, Q would always stay negative as you are rotating around because we are always defining it, relatively to that length. But we're going to get there really soon. We'll see when we look at the whole sun. As you said, that falls down and the things change. Yes. So we somehow define axes for Q and U, which are stable. Then yeah, if I, for example, move to this limb here, my Q becomes positive. If I move somewhere in between, Q and U change meaning and so on and so on. Okay. So this is what we call all these things are something that I like to call, and that we generally call, single scattering approximation, right? The atoms are illuminated by some radiation field. They scatter these photons once. I collect all these photons. This is basically my solution of the radiative transfer equation. I'm not solving any differential equation, nothing. I just multiply source function, which is equal to the intensity, times the opacity, and that's my observed intensity. End of story. That's single scattering approximation. And single scattering approximation, the polarization is created in that single act of scattering that we are talking about since the start of this lecture here, right? So one thing that we don't have to worry about, we will talk about it, is that in principle we could, extend this and integrate. So basically what we're going to talk about now is how in this single scattering approximation I finally find that polarized source function that I introduced a few slides ago, but didn't still get. Okay. We said that this is the problem. I need to fix this outgoing direction, have some Q, U, I, and V there defined in absolute sense. And for incoming directions, they're always going to be defined relative to the direction, so there's nothing that I can do. So I need to fix at least one thing. But you all feel that conceptually, to get, if my point here is illuminated by multiple rays or by some continuous distribution of radiation, to get this emergent intensity, I will have to integrate over the all incoming directions. Okay, I think that makes sense. That's typically what we do. Without further ado, I'm going to write it like this. Say that my outgoing Stokes vector, I'm not introducing source function yet, but I will real soon, is proportional to integral over all the angles of the incoming Stokes vector times something called scattering matrix. This time, this scattering matrix is a little bit different than the one we drew previously, because now this describes angles in some predetermined system, right? I fix my X, Y, and Z, and I have some incoming direction, outgoing direction, which are fixed. I'm not thinking about these planes at all anymore, right? Not on the surface. And I get this function here, which tells me exactly how the incoming Stokes parameters are transforming in the outgoing ones, and I'm integrating over that. Now, I don't be confused by this theta vector. Theta vector is just pair, omega vector. Omega vector is just pair theta phi for the inclination and the azimuth of the radiation. So what are we doing here is basically we're fixing our coordinate system. We have some ingoing, outgoing radiation directions, which are well defined, and we are coupling incoming to the outgoing intensity through this. Okay. That's it. Question is, of course, how this thing looks like. And we kind of have to agree, we kind of have to make peace with the fact, as I said before, that simple scattering, I said simple, I mean continuum scattering cannot create Stokes V, but that it can in principle create Stokes U. We saw example previously. If things are coming more from one side than the other side relative to my fixed coordinate system, I can get Stokes U. It's not amazing. And finally, we got the answer. I kind of jumped to this derivation here, but this shows you why the polarized source function is angle dependent. This matrix here, this scattering matrix here, looks different for different outgoing. The big complication, big difference compared to scalar case. Now we're going to try and see what else we can. There's a lot of painful things here. Is that now if I have multiple outgoing directions, I need to recalculate all this again and again, because this scattering matrix here changes. Or I would just integrate all my intensity, get this scattering integral, be like, cool, this is isotropic, this emits equally in all directions. I just need to integrate my, radiative transfer equation along these different directions, and maybe I'll get different results, but that's fine. Here, I need to recalculate this integral, and it's going to be different for each outgoing direction. And that's annoying. Another annoying thing is that this matrix here is very complicated. It looks very ugly. We cannot discuss physics looking at this matrix directly. So we're going to look for a simplification. And at first, it's not going to look as a simplification, but I really like it because you get to use this command in LaTeX, which makes things nice and pretty. And you get to use these that are going to do one very nice thing. They're going to decompose this matrix, incoming part and the outgoing part. I write in a way, a little bit more complicated way. I'm going to write my Rayleigh scattering matrix as the product of two tensors, where one depends only on the direction of the incoming radiation, the other one depends only on the direction of outgoing radiation. Some of you are already feeling why that is important, but I'm going to walk you now very, very slowly through that. And there is a full derivation in the book by Landi, Deglino-Centi, and Landolfi, and in a lot of papers that have been written through 90s and before that and so on. People try to use it to illustrate simple two-level atom models, and it works very nice. Okay. So the main thing here is, and this plot here only describes the outgoing radiation field. To describe the outgoing radiation field, we need to know with its azimuth. I'm going to use a different letter for the azimuth because I already spent chi for my opacity, and I don't like using chi for azimuth. And then this angle gamma here, which defines what? Which defines what's my positive and negative Q. Right? This is a pain with polarimetry, that I need to know what's my referent direction for measuring linear polarization. And you will see later when we use Hazel, we'll have to define this gamma, because this gamma will influence what positive Q, what negative Q means, right? And when you want to interpret the observations, you need to know how the observers define this gamma for themselves. Good. Okay. So how does that look? Well, it turns out, without further ado, we're just going to jump in there, that you can write your scattering matrix, which is the thing that couples the polarization of your incoming and outgoing radiation, as sum over different combinations of these number K and Q, so-called multipolar components. They work like this. K goes 0 to 2, so it can be 0, 1, 2. Q goes from minus K to K. Total, we are not going why that is so. We are just accepting this the way it is for now. We can go into the book and look at the derivation, but it's too long. We want to use this to understand values that we are getting. Okay. The total number of combinations is Q goes between minus K and K. Well, for K equals 0, Q is 0. For K equals 1, Q is minus 1, 0, 1. So that's 3. And so that's 4 in total. And for K equals 2, Q is minus 2, minus 1, 0, 1, 0, 1, 2. So that's 5, 5, and 4, 9. 9 quantities in total. We're going to look later how they look. We're going to see later how they look like. But what's important is that we can write it like this. And for the moment, you are like, why is this guy showing us this? This is terrible. This is ridiculous. What is this sum? What are these K and Q? This Q is not Stokes Q to increase the confusion. This is just some number Q. Super painful. Let's see first what this equation, what is which thing in this equation, and then we're going to try and figure out why I introduced this at all. So, get my scattering matrix. I'm summing over these, 9 possibilities. For some reason, I have this alternating minus 1. I have these two quantities where one is related to the incoming direction, one is related to the outgoing direction, and I and J refer to Stokes vectors. J is incoming to the components of the Stokes vector. J is incoming, I is outgoing. If I is 0, that means I'm talking about Stokes I. If it's 1, talking about Q, 2. Okay, and the same for incoming radiation. What I have to do, and also I should also sum this over yeah, no, actually I shouldn't do that. I will sum later when I introduce the source. Right, looks like this. Why in the name of God am I doing this? Does anybody have an idea? Why am I bothering you with this decomposition of some complicated matrix into more obscure quantities? There is a very good reason. Whoever has the idea can speak up. I don't. Simplifies why? Very good. Very good. Integral is only over the incoming angles. So I will be able to pull this one part out, leave other things inside of the integral, and once I integrate them, I don't care about them anymore. I just, as I like to call, project them on different outgoing directions, and I'm good. It will also allow me to explain you what are the necessary ingredients of scattering polarization. We need things to conspire in order to see non-zero scattering polarization. Good. Well, let's go there. Good. What I'm going to do is I'm going to walk you slowly through these equations here. First thing is that get, because how this equation here works, each component of the source function is going to have contributions from each component, meaning IQUV is going to have contributions for both IQ, U, and V of the incoming radiation. Means that in principle, to get my source function for the outgoing radiation, I'm going to just replace for the moment the scattering matrix with this sum here. Then what we're going to see? We're going to see depends only on the outgoing radiation can go out of the input. Minus 1 to the power of Q can also go out. Well, what stays in the integral? This thing, depending on the incoming radiation, times the incoming radiation. In principle, now I should have one more sum over J here, because for each source function, I'm summing over these things. But typically, we're going to assume that incoming radiation is unpolarized. So I'm only going to be considering Stokes I. Okay? But in principle, and you will see me later at some point putting J here, so small j, for incoming radiation. The way I can write it is I can define this source function that is angle dependent as the sum over Q and K of this factor here that describes outgoing radiation times some new quantity called SQK. SQK doesn't depend on any angle anymore. Why? Because I integrated over the incoming angles and I separated out the effect of the outgoing angle here. Looks like gymnastics, but computationally and conceptually it's going to be super easy. This is just for reference what remained in the expression. SQK. 1 over 4 pi as the averaging, minus 1 to the power of Q, integral over this thingy. What's on the next slide? So, if you with me, if I said this part here depends on my view in geometry, depends on where am I looking, from which direction I'm looking at what's going on. Make sense? One is not approving. 3? So, huh? Well, I is my outgoing Stokes vector. So for IQ, U, and V, I'm going to have different values of that. Chi is the angle that describes my outgoing direction of radiation, right? So this depends basically where I'm standing, right? If I'm standing here, I'm at theta equals 90 degrees, phi equals 1. If I jump on the floor, I'm on the ceiling, I'm going to be theta equals, 0 and phi equals something. If I lay down, I'm going to be a theta equals pi and so on and so on. Okay. Then agree that this thing SQK here depends on the angular distribution of the coming radiation. Only on that. It doesn't depend where I am. It actually depends how the radiation is, how the illuminating radiation is distributed over there. Okay. And this is why I say the following, that that there are two things that determine scattering polarization you will see. Some, what I call casually here, projection factor, that depends on the irreducible spherical tensor for the outgoing radiation, times some measure of anisotropy of the illuminating radiation field. These are two things that are necessary for us to see scattering polarization by some object. Radiation that is illuminating it has to have this integral equal to non-zero, different from 0. And we need to be in a favorable position to see the polarization. I will convince you that, I will give you examples where one of these things is true, the other one is not true, and we see no polarization. And we will agree on that. It will be a little bit clearer then. Okay? Okay, good. So yeah, this is the thing. This is what you need to do. And this looks terrible, but at least now you know. Now you're like, okay, if I want to calculate scattering polarization from something, I need to know my illuminating radiation field, integrate that times some horrible thing, and then multiply that times some other horrible thing, and I will get it. And it's horrible, and it takes, time, but it's doable. That's the main point of this, is that this is doable. It's not end of the world if we go through this. Good. So how these spherical tensors look like? I'm going to actually walk you through them now, because we will use them to interpret what we see. This is the spherical tensor for the intensity. And there are 4 more, and you can use this transformation here to get the one with negative Q. 5 of them in total. And typically for linear polarization, all these things where K is 0 are 0. Just example of these. I'm not going to go through this one now, because I want to actually show you one for outgoing radiation in Q. Right? And this is basically the sum of all the things that we have shown just now, that the observed scattering polarization depends on the viewing geometry and on the anisotropy of the scattered radiation field. Good. So what I want to do now is I want to look at the equations for spherical tensors, analyze what contributes to these two terms, to my viewing geometry and to my anisotropy. So let's start with this one here, with the view. This is our setup. We're going to put ourselves along a given direction. We're going to look at the slab, however you want, that is only emitting by scattering. The radiation is thus going to be polarized because we accepted that scattering creates polarization. We're going to assume that we know the incoming radiation field, that we can calculate it, but that the incident radiation is unpolarized. We know already that, incoming unpolarized radiation fields still can create polarized radiation, and we're going to only look, and important thing, I'm going to assume that incoming radiation field depends on the polar angle, right? It's different for different thetas, but it's axially symmetric, right? Do you agree with that? If I'm above the sun, very far away, and sun is just a uniform blob, uniform ball, I'm not going to get equal amount of radiation from each polar angle. Sometimes I'm going to get light, sometimes I'm not, but axially, everything is going to be symmetric. Is it okay? Right, good. And I'm going to look at this equation here. I'm going to assume for the moment that SQK is something. And I'm going to see what these projection factors tell me about all these things. And one good thing is that for outgoing radiation, T00, T01, T11 are all 0. One that I want to focus right now is T02, equal to -1, 3 over 2 square root of 2 for some reason. sinus squared theta. What is theta? Theta is my polar angle of my radiation. Okay, interesting. And it also depends on the gamma. Does anybody remember what gamma is? Yep. Reference direction for measuring linear polarization. Typically, our gamma is going to be 0, so this factor here is going to be 1. And for the moment, I want to focus on this thing here. Later, gonna convince you that these two, looking scary and complicated, are not important for our case right now. Okay, so what I do is I'll do like this. I'll say that my Q, finally some Stokes vector, something specific, equal to, oh look, optical depth, nice, times this projection factor, and the source function for that projection factor. Cool. And if I write it down, and finally, it's time to introduce something new, because we said that source function only comes from the scattered radiation. I'm going to replace S02 by J02. And now you finally know in all these fancy scattering polarization papers where somebody says J02, you kind of know where that comes from. It comes from the multipolar decomposition of the scattering matrix and thus the radiation. The way I'm going to do that, here is my projection spherical tensor here. I'm going to say that my linear polarization is equal to this thing here, times J02. I'm going to replace, I'm going to set this cosine 2 gamma to 1. Since we set gamma is 0, I'm going to say minus 2 theta is, and the minus here are actually mu squared minus 1. Wow, another familiar thing, mu. You remember what mu is? The cosine theta, right? So sine theta is, sine squared theta is 1 minus cosine squared theta, which is 1 minus mu squared. And then when I swallow this minus here, I get mu squared minus 1. I bothered you a little bit with this, but now it shouldn't be a problem for you to tell me what polarization this observer is. Looking from above, mu is equal to 1. Does everybody agree? You remember what the equation said? Something, something, something. Mu squared minus 1. Mu squared minus 1 is 0. Trust me. It is. Mu squared minus 1 is 0. 0. How come? I have an object that is scattering everything, right? And yet I'm looking at it and seeing 0 polarization. How do you interpret that? The way we can think about it is we're looking here, we're looking at the disk center, radiation coming from all directions, polarized polarizations cancel in a way, right? I mean, here I have more Q, here I have some other sign for Q, all things are canceled. This is related to what Ryan asked earlier. When we move around the circle, our Q and U change, right? And here we are in the fixed reference direction, looking at the disk center, and in principle, disk center is unpolarized when everything is nice and homogeneous, when we only have J02. Because our main assumption that J02 is the only factor in the full story. We don't know yet what goes into the J's. You're already anticipating that there are other J's. There is J12, J minus 1, 2, and so on and so on. We don't get there. This is our next step, right? But this was important to find this projection factor, to convince ourselves that even though we're looking at the scattered object illuminated by an isotropic radiation field, God, we should have been done by now. Okay, I'm done in a minute. You don't have to think about this one, you know the answer, but we are making a break now. See you in 10 minutes, right, Rebecca? More. All right. I think this is good. We can leave at this plot and we can go back to it. Yeah. I thought I set the alarm for 2:20, but maybe I set it for 2:20 a.m. So yeah, we can have a short. Do you want to have a Q&A session maybe after the end? Right, yeah, sure. We can leave it for tomorrow, yeah. Yeah. Let's take a 10-minute break and we can continue. Yeah. We are on a good done in time for dinner almost. Okay, so I think everybody's here, so we're going to continue. One small correction that that Yingji reminded me about. So once again, here there is a missing sum over all different those components, right? There's sum over that. So in principle, it should imply that I'm summing this j with j that enumerate this I here. Doesn't matter for us now because we're going to be assuming that we are only looking at j equals 0. We're only looking at the incoming radiation that is unpolarized. But in principle, when we want to solve full so-called non-LTE problem of the second kind that I will mention on Friday, we need to take these ones into account. They're maybe not crucial, but in principle, they should be count. And the more anisotropic your medium is and more polarization you have, the more important they become. And the polarization of incident radiation, I mean. And then we were here, right? We said that now looking at mu equals 1, this factor here is -1, right? So I know that if J02 is something, my Q is something. I still don't know if it's positive or negative, right? Because contrary to J, which is actually J00, which is our scattering integral, our mean intensity that is positive by default, we will see that this doesn't have to be. This can, in principle, be negative. There are, let me run ahead a little bit. There are, in principle, there could be a setup where you have spectral lines that scatter the light and it's oriented positive to them. It would have to be a lot of physical effects conspiring to create that, but in principle it could be possible. Right? The only thing that I want you to pay attention to here is that Q at mu equals 0. So here I put 0 is tau lambda, so it's proportional to the optical depth. We kind of imply that, we didn't prove that, times this geometrical factor 3/2 square root of 2 times mu squared minus 1. And then I ask here, how would you calculate fractional polarization? What is fractional polarization? Ratio of Q to the I, okay? What are the same things here for Q and I? What do they share? Which parts of this equation? One, which one? Same for Q and U. Root 2 is not, because I is commented by J00. This is determined. This also not, right? When we were deriving things for slab earlier, there was no this projection effect. 3/2 square root of 2 also didn't appear anywhere. Only optical depth. Again, something that we kind of just said, well, it's going to be proposed. Technical term for this is saying lower level, the level that determines the opacity, is unpolarized. Otherwise, it can do various kind of things. But later, we're going to move all this to quantum realm. We're going to describe this using some quantum terms, and then we'll see what happens. Okay, so now our next task to see if things make sense is to determine whether J02 is positive or negative. Okay, we want it to be positive. Why? Because we said that Q is minus something, 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 and we expect it to be negative. So we want Q02 to be positive so that our Q can be negative. Okay, so let's look what J02 is. And just a reminder, this would be our geometry here. And here now there is no thing that we talked about before. There is no, radial symmetry. There is prominence here, and it's, illuminated like this. It's scattering toward us, and we see it polarized. And it's true. Here is a calculation by Kahn et al. Actually, the author of the Bible, Egidio Landi, is here, and Luca Peluzzi also. And here they are calculating the polarization of Lyman alpha line around the sun, corona, and it's always parallel to the solar limb. But, and Ryan asked this earlier, if we integrated this whole image here, polarization would be 0. Because this polarization here and this polarization here would spatial resolution to see the polarization. As a whole, sun is unpolarized due to scattering polarization, at least. Okay, so 2. Have non-zero Q, we need favorable geometry, and we need non-zero, I call them source term here, JQK or SQK or however you want. So now let's have a look at what J02 and other J's are. And here I'm asking you, when will for sure they all be 0? For what kind of radiation? We're already anticipating. What kind of radiation gives us all J's equals to 0 except J00? Somebody said it? Just say it louder. Isotropic, exactly. So if the radiation field is isotropic, we expect these things to be 0. What's the motivation behind that? Well, the motivation behind that is that when things are isotropic, there is no preferred direction for electric field to oscillating, right? And no matter how favorable my geometry is, although when things are isotropic, there is no favorable geometry after all, right? So now we are going to look at the source term a little bit. And source term is this. Okay. Minus QK, this is going to, we're only going to look at J equals 0, and here we're going to look at the polarized intensity, unpolarized intensity. Cool. Well, for that, I'm going to look at the spherical tensors for the Stokes I. How do they look like? Let's dig into them a little bit. So S00, I'm going to have 1, and that's going to reduce to my quantity. Is that going to be? No, it's not going to be I because there is integral still. In intensity, right? The regular J, the J that we saw before, just integrated intensity over all the n. Okay? This is why sometimes casually I call these things moments of the radiation field. Why moments? Because I have the radiation field dependent on the angles, and then I'm multiplying them by something. It's kind of like moments in statistics. So look at this. T01, T11 are 0. Well, that's okay. They were 0 for the projection factor 2, so that's neat. Everything is very consistent, but now these things here are non-zero, right? Here we see that for J, to get S02, which is J02, I need this thing here. We ignored for the moment J12, J22, J-12, and J-22, but they are also in principle non-zero. In principle. Now I'm going to write it out, assuming that only intensity matters, and I'm going to write omega as theta phi, and I'm going to write what d omega is. There's a lot of equations here, and we're going to look at them together step by step. Okay? Hopefully, cool. So as I said, when I plug this one in here, I get J00, which is just the integral of the intensity over all possible angles, which is just mean intensity by the definition. Same as J02 is 1 over 4 pi. I take this in front, and I get 3 cosine theta squared minus 1 times intensity times this thing here. One that is most important for us now, but let's discuss these two. Okay. These are the two that we didn't consider before. I told you we're not going to consider them right now. Can anybody look very carefully and tell me why we can safely ignore them for our simple example? There's something that makes them 0. Exactly. So this thing here, e to the I phi, since I'm integrating over d phi from 0 to 2 pi, this thing is going to cancel out. So these two for the axial asymmetric radiation field are going to be 0. That's the reason why I Forgot about them. But of course, if your radiation field is not axially symmetric, then you cannot assume that. Find that there are two terms. One has period 2 pi, one has period pi. One is 2I pi. Complicated thing. Good. These two also have their negative twin siblings, as I say, J minus 1, 2 and J minus 2, 2, but they're also 0, right? Because of this thing. Good. So now I will combine it with the projection term, right? And also I want to note that gamma, our definition of the Stokes vector, doesn't appear in the source term. Why not? Because it's always going to be locally changing with the plane, so it doesn't make sense for me to define it. It doesn't depend on the outgoing one, right? So now I'm focusing on this thing here, right? And we also said that, right, I need to, so now what I'm doing is, now these are again spherical tensors for Q. Okay, so my Q, my observed Q is going to be this thingy here times this J here, right? Proportional to that. So there's a lot of angles and things. And about these things, I can forget for now. And you can now make things more complicated, make any distribution of the angles that you want, and so on and so on, and solve it, and it will work out, right? But overall, it is possible. It's nothing. It looks ugly, but it's not conceptually hard. I just want to convince you that for our case, when mu is just coming, when radiation is just coming from mu equals 1, J has to be positive, right? Because only mu equals 1 matters. This is 3 minus 1, 2 positive times intensity that's positive. This ends up being positive, right? And in principle, in our case of things illuminated from below, which is from larger mu's, this is going to be positive here. Our Q is then going to be negative, if you remember what we said. What happens? This is how it works. I give you incoming radiation, calculate these things here, and you multiply them by these things here, add sum over QK, and you get your Q. In general, it's a little bit more complicated because here you should now add other polarized components if your incoming radiation is polarized and so on, but we're not going to go there. Tells you what's the story behind. That's it. Main takeaways are these ones. Scattered radiation depends on the incoming radiation field and your viewing angle. I'm calling it here scattering angle. And in single scattering approximation, we literally just integrate over all the scattering directions, and that's it. And the coupling term that couples the incoming and the outgoing radiation is called scattering matrix. Force function that you end up with when you do that is anisotropic. What does anisotropic mean? It depends on the outgoing angle. It's not the same for each viewing direction. And we can kind of simplify it by introducing these irreducible spherical tensors that nicely decouple incoming and outgoing radiation. They're a little bit of pain in the neck because of their ugly expressions, but today your computers handle that anyway, so you don't worry about it. In principle, right, I could make this more complicated. I could say, I find the source function in multiple points along my line of sight, like if I'm in Corona, for example, and then I integrate over that and I get the result. I can also do that. I can make things more complicated if I want. And later, we're also going to talk about the coupling, about the non-LTE-like problem, just for this. Well, here's a question for you. You don't have to answer it now. You can answer me on dinner. So if the source function is anisotropic, it means that intensity is anisotropic, right? But is the opposite true? Think about it. Let me know. I'm not going to. Right. So we are supposed to talk about spectral lines, after all. All these expressions were somehow derived for continuum scattering. And now I'm just going to jump and say, well, this all applies to spectral lines, and we're done. Not quite, because I want to convince you that this also makes sense when we take into account quantum physics. Okay? But in principle, this very much applies. And this was the difference, remember? Once again, this was scalar case again, very simple. Source function was equal to the, again, integration of the intensity over the angles times this factor here. This implies the so-called complete frequency redistribution. Interesting thing, if you didn't notice, Rayleigh scattering matrix does for angles what frequency redistribution does for the frequency. Frequency with a PRD is correlation between the wavelength of the incoming and outgoing photon. Rayleigh scattering matrix gives you correlation between the incoming direction and outgoing direction. Conceptually same. And in general case, PRD is also angle dependent. So you have a matrix which coupled for the directions and wavelengths, but we're not going to go there. All right. We have that. So I'm just going to apply it to scattering polarization in this nice concise form here. Polarized source function is 1/4 pi. I'm writing it again as redistribution matrix because I don't want to waste space on spherical tensors. I know that I can decompose it if I want, times intensity, times the line profile. This is new. And this is exactly true for the case of atom, or actually transition, which we call normal Zeeman triplet. What is normal Zeeman triplet? It's the simplest possible, well, not simplest possible, but the easiest meaningful possible transition, where the lower level of the transition has J equals 0, and unsplit. If we are now thinking about Zeeman effect, it's unsplit. Upper level has J equals 1, and it's split once. So the lower level can have only one possible value of M, which is M equals 0, so it can fit only one electron, sorry. The upper actually can fit electron in one way. The upper level has J equals 1, so M can be -1, 0, 1, so it can fit the electron in 3 ways. And this, having this lower level unsplit, or J equals 0, is what we call the lower level is unpolarized. We will see soon what it means to be unpolarized. And also, we will neglect for the moment magnetic field, so these levels are not actually split. We know that there are these different M's living within there, but they are not separated in any way. And there is also something called Hanle effect or Hanle rotation, but we don't know yet what Hanle rotation is, but soon we're going to. Okay, so before we go there, what is the main difference in formalism, in the story between the Zeeman effect that creates polarization, and it can also create linear polarization, and Hanle effect? Oh, sorry, not Hanle effect, scattering polarization. What is the main thing? How does Zeeman create polarization? What happens? Level split, and then there is, for some of the terms that you heard from. Actually, in Zeeman effect, we never talk about the de-excitation. We only talked about primes with no. Selective absorption. No? Okay. Optical effects you heard about. Did you hear about what's the name? Dichroism. Okay, so what we have is that different parts of the spectral line absorb different polarizations, right? That's why Zeeman effect creates the polarization. Emission has nothing to do with that. Emission was unpolarized. Why was emission unpolarized in David's lecture? The cause for emission there. Thermal excitation, right? Your atom would collide with something, it would get excited, it would emit light, that light would be unpolarized. There is no reason for that light to be polarized. The reason why Zeeman effect polarizes the light is coupling in the absorption matrix between the components, which creates polarized radiation. We were talking about this in a hike, right? Lux V appears because one wing absorbs more one circular polarization, other wings absorbs more other circular polarization. So we get this nice thing in there. Here it's completely different. I get polarization even in the absence of any scattering matrix, right? There is no magnetic field. K is just 1, 1, 1, right? But my emission is polarized because my emission is described by scattering processes that emit polarized radiation, okay? This is the main conceptual difference between these things here. Good, yeah. And in principle for Zeeman effect, if we talked about that enough, but for Zeeman effect, he didn't care much whether we are in LTE or non-LTE, right? The main fuss was to get level populations, But then we split them, and then we get our Zeeman or Paschen-Bach effect, and then things are easy, right? In scattering polarization, the emission is polarized, right? Scattering polarization requires non-LTE, right? LTE lines, LTE phenomena cannot result in scattering polarization. Scattering is, in a way, non-LTE. Non-LTE is a more sophisticated version of scattering. In reality, though, we can have, and we do have, both Zeeman effect and scattering polarization, and then you have both your non-diagonal absorption matrix from the Zeeman effect, and you have your polarized emission, and you need to take into account all these incoming polarized rays when you are calculating that polarized emission. It's still managed, right? And here is a real-life example of the changes. Finally, some observation. This is real-life example of how regime in the spectral lines changes from the Zeeman effect to scattering polarization. First of all, here we see our observing geometry. We are very close to the solar limb. Why are we close to the solar limb? The smaller our mu is, more scattering polarization than up. And our slit here is partly over a magnetically sensitive region and partly over the quiet side. The lower part of these Q and dots corresponds to the magnetically sensitive region. Upper part corresponds to the quiet side. And you can see that the intensity, there is almost no difference, right? Things are very homogeneous along. Intensity along the slit is very homogeneous. However, for the Stokes Q, and I want you to pay attention to this line here, famous strontium 4607 line, and when you look here in the magnetical region, you see negative, positive, negative. Good old Zeeman effect, right? Negative, positive, negative. Same thing in the Stokes U, negative, positive, negative, and here maybe even some positive, negative, positive, which means that the azimuth is changing, right? And finally, here in the Stokes V, you see positive, negative, and in this line here next to it, this is iron line next to it, positive, negative. So gold and effect signature. But outside of this magnetically active region, as the magnetic field is getting weaker and weaker, which we can detect from weaker and weaker Zeeman effect, our Zeeman signature in strontium line changes from negative, positive, negative to just positive. Going from the regime of Zeeman effect linear polarization, scattering polarization. Scattering polarization would be there even if there was no magnetic field whatsoever. It will be there because there is some short term, there is some anisotropy, and we are in the favorable geometry. We are close to the solar. If it or not, this spectral line is not in the corona, not in the transition region, it's not in the chromosphere, it's in the photosphere. Photospheric spectral line that exhibits scattering polarization. That's why it's, as you say today, older age, because it gives us complementary information to all these other photospheric spectral lines that we have been talking about. You know the lines, HMI lines, MDI lines, solar orbiter lines, sunrise lines, and so on and so on. Right? You can see here that it's very peculiar, though. It's the lines that show scattering polarization outside of this specular region here. Else is nothing or something little, right? Very nice. I will show you on Friday some even more convincing observations that deal with this line and more fresh, like from. So what we're going to talk about now is spectral line scattering with some quantum and classical, insights and ideas, and we're going to go through it and just see whether it makes sense with respect to the things that we have just learned. What we have just learned is we learned a lot of things for the continuum and just said, well, it applies to the line. But we're now going to see if it makes sense. Okay. So first of all, you heard me say this thing a lot of times, normal Zeeman triplet. I summarize once again what it is. Let's just remember what it means. Lower level has angular momentum quantum number equals to 0. So its total angular momentum is 0, and its projection of angular momentum on predetermined axis, which we call quantization axis, can only be 0. The upper level that is 1. Its projections to the quantization axis can be -1, 0, and 1. That's what we remember from quantum mechanics. And we know that when we turn I call them Zeeman sublevels. Why do we call them Zeeman sublevels? Because when you turn on the strong magnetic field, these levels split, right? They stop being what we call degenerate. When there is no magnetic field, they all overlap in energy. We call them degenerate. When we turn on magnetic field, they separate in energy. They're not degenerate anymore. Here I say that they're completely identical in the absence of the magnetic field. But what I'm going to try and convince you is that they are not. The reason that they are not is kind of given up in this sketch here, where different directions of the magnetic field, different directions of the incoming and outgoing radiation imply different sub-transitions, as I like to call them. And it's going to take us some time to decipher what is happening here, but this is some of our, this is our geometry here. We're looking from the above. Our atoms are here. They are overshadowed by this arrow pointing to where magnetic field is. And by magnetic field, I don't necessarily mean magnetic field. I mean direction for my z-axis. Magnetic field can be 0, can be 1 million, but it's always going to be my axis to determine m, right? Of m is possible projections of the angular momentum on this axis here. And you can forget about these oscillators and these circles here. We're going to see later what they mean. To understand what is going on, we need to introduce what happens with the photons. So photons are coming and going, and believe it or not, photons are bringing or taking away some of the angular momentum to the system. Projection of the angular momentum of the photon on the given axis, think that it can be -1, 0, or 1, but it actually cannot. It could be -1 and 1 because photons are massless particles. And the reason why that is so, when Roberto comes back, we can maybe ask him for, there is an intuitive reason, but for the moment I don't know it. So they cannot carry 0 angular momentum. On the given axis, they're even plus or minus. Allows us to understand why, when you're looking along, when you're looking at the ray of photons, you don't even have to look. If the photons are propagating, let's say, upwards along Z, can only be absorbed in the transition from 0 to -1 and from 0. Only 2 out of these 3 sub-transitions are possible. Why? Because photon is carrying some angular momentum. And if the photon is absorbed, the angular momentum has to go somewhere. How does it go somewhere? It goes somewhere because m is changing. Delta m equals 0 along this axis here. It didn't. The reason why, now try to remember what David and Carlos were showing you. When magnetic field is pointing along the line of sight, and you're looking at 6302 line, that I think it has very simple configuration. It only splits into components. Remember that? Or maybe not for that specific line, but you remember for some line that it only split into components. See what happens. If I just look at the radiation coming along this, only these 2 sub-transitions are going to be allowed. Here I'm calling them in quantum mechanics notation 0, 0, 0, -1, and then 0, 0 to 0, 1. So delta m equals -1 or plus. Sorry, my bad. This is 1, 0, and 1, 1. I will add it. Thanks. Right? But this is simply conservation of the angular momentum as for this. Okay? Way for you to simply understand why that is happening. Nice. And you can understand Zeeman effect that way. One component absorbs one circular polarization, absorbs, for example, actually, these 2 angular momenta carried, these 2 possible angular momenta carried by photons are 2 circular polarizations, positive and negative one. One component absorbs one circular polarization, the other component absorbs the other circular polarization. That happens anyway, but they are indistinguishable, so they just absorb. But when I turn on the magnetic field, they split. Their absorptions shift in wavelength, and I get this thing here. One component absorbs more negative, so positive remains. The other component absorbs more positive, so negative remains. I add them together, I get this signature in the Zeeman effect. Less possible quantum explanation for why Zeeman effect happens. For that, you don't need anything to emit. You can just consider absorption. You're still going to have Zeeman effect. If I have super cold slab, not emitting, just absorbing, turn on magnetic field in it, I'm going to get Zeeman effect. Not that easy to make the same explanation for linear polarization. I'm going to give you a different explanation for linear. But what I can do is I can at least explain to you why these photons are absorbed in the way they are. That I'm going to take these photons. I'm going to now imagine that photons are coming, for example, along X. And I'm going to say, well, now they are either plus or minus. They have either plus or minus spin along X, but I'm going to write that spin in Z coordinate system. And you might remember these transformations, quantum mechanics class. I helped somebody teach quantum mechanics last year, so this was kind of fresh for me, and it was very 1 over 2, 1 over square root. 1 over 2, 1 over 2, 1 over square root. Now how can I picture this? I can picture this, that when photon is coming along X and being absorbed, excites some linear combination of my upper states. And by squaring the coefficients in these, in front of these eigenstates, basically, of my upper level, I'm going to get how strong the absorption is for different one of these. Which means that in this case, I'm absorbing twice as much transition 0, 0 than 0, -1 and 0, 1, right? Which explains why, when we look at the Zeeman linear profiles, there are 2 small dips and then a big one of the opposite side. We cannot quite understand the signs of these linear polarizations yet. We will do that soon by looking through the classical picture. But this tells you very nicely why the ratios are like this. We're later going to see that this also matters for scattering polarization in the quantum picture. Okay? So this was just to convince you that photons do carry angular momentum, and the whole story, the whole explanation behind what all this happens hides in the interaction between the angular momentum carried by the radiation, angular momentum of the atom, and how these things interact and are conserved. That we had here. Here we had, if the radiation is coming from underneath, it only excites this and this one, right? Polarization is coming from the side, it excites the middle one, 0, 0, twice as much as 2 other ones. This results in something that we call uneven population sublevel. So in the case, if I illuminated Rhomatom from underneath, I would get more of these than of these. And that I would get more the exciting. Here, then from here. Anybody guess now why is non-LTE important? I don't have my upcoming slides, so I'm kind of winging it. I had some point I was to ask you this, so I'll just ask you right now. Okay. Why is non-LTE important? At this point, I'm going to say non-LTE is important. Why? Why are these things unevenly popular? Because of the radiation field, right? Okay, so radiation field is the one that's exciting the atoms here. What is exciting the atoms in LTE? Collisions, and collisions, the way we picture them, are always completely homogeneous and isotropic and so on, so they will populate these things equally, right? And I cannot get this uneven population, I cannot get this uneven emission from here. We still don't understand why this uneven emission leads to polarization of the light, but we are all somehow feeling it, right? Okay, just to note, also the lower level, you don't have to have normal Zeeman triplet. In general case, both are split. But this is just to show you that in principle, I can have a lower level that is split, upper level that is unsplit, And again, I'm going to have similar story. Radiation coming from below, only these two are depopulated. Radiation coming from the sides, this one is more depopulated than these two. So again, I have some imbalance. This imbalance, these different populations of the Zeeman sublevels is what we call atomic polarization. So, and there is more to atomic polarization than just this, but the simplest case of atomic polarization is when you have uneven population of the Zeeman sublevels due to the presence of the anisotropic radiation field. Of course, what happens in the real life is not that I have radiation just coming from below or just from the sides, but it's coming from all the sides, but in different amounts. So eventually there is like a mixture between these two. Right? Cool. So what we have is this one. Different illuminations from different directions excite different Zeeman sublevels to a different degree. And this is all the consequence of the conservation of angular momentum during the absorption process. And what we end up with is our populations being uneven. And this is why non-LTE is important, because if we were in LTE, collisions would wipe this all away. They would polish all your level populations, all your things according to Boltzmann distribution, according to some simple law, and none of this would matter, right? This is why it was so important for me to convince you that the emission coefficient, even for scalar radiation, depends on the incoming radiation. Same thing here, but I'm not talking about the populations of the levels anymore. I'm talking about the differential population of the sublevels now, which is also determined by the incoming radiation field. And if it was determined by the collisions, it wouldn't exist. Everything is isotropic. And if you remember the source function for the Zeeman effect for LTE, it was just source function for I, that was Planck function, and then 0, 0. Here's another type of things that destroy this uneven population of Zeeman sublevels. These are the so-called depolarizing collisions. Polarizing collisions are elastic, and we'll talk later about what being elastic versus non-inelastic means. Okay, good. Let me see what time it is. Oh, we have like 40 minutes more. Okay. So now what I want to do is I want to see how I can kind of use uneven populations of the upper level to formulate some sort of source function for the polarization. We're all feeling it, right? We're all feeling that this uneven population of the upper level results in polarized emission, results in non-zero product. And this is just a reminder for our non-scalar, for our scalar story, non-polarized story. This is the first time that I'm writing this equation, though. There is extra for pi. I will try to remember to delete it. But here, my emission coefficient from polarized radiation is equal to some constants, population of the upper level, times Einstein coefficient of spontaneity. That population of the upper level is proportional to the radiation. And in the scalar case, this is the scalar case, population of the upper level is determined by the mean intensity, by J02. Polarized case, sublevel imbalances, the thing that I have been talking about now, are determined by the anisotropy. First possible case by J02. Now we're going to talk about why emission looks the way it does, why these specific subtransitions emit polarization of different signs, and how that all conspires to create some net linear polarization in the scattering process. This is something in between quantum and classical picture, called Introduction to Modern Optics, which is an amazing book, small like this, contains everything. $5, I suggest everybody get it. The author was one, head of the US Optics Society for years and so on. It's wonderful, really good once you know everything to remind yourself and look for very nice explanation. So how he pictures that is he says, well, I have these transitions. Here he says I have 2p, which is like k equals 1, right? Kinda. And 2s level, which is lower level, which is j equals 0. This is how my probability functions look like for these kinds. probability density for my excited state here, right? And this for 2s for 0. And my lower level is also going to have this, right? Get the transition from this state to this state. Maybe remember this. You saw this at some point. This is how we sketch our things. Like we don't know where electron is, but we kind of know its probability density. Now there is a wild concept. We discuss what happens during the act of emission. Never discussed this before. We talked what happens before the atom emits. We talked what happens after the atom emits. But it turns out that a nice toy model to explain how the atom emits is to say that during the emission act, it's in some coherent superposition of the lower state and the upper state. And the probability of finding it in one and the other state varies with time. Why does it vary with time? Well, because if I write my state as a superposition of the lower state and upper state have different energies. According to Schrödinger equation, this is how things evolve with time. But now these coefficients in front of the time evolution are different. So when I square this, it's going to be a function of time. Way to show how that happens. So if I have probability function of finding my electron changes with time, it's like my charge distribution changing with time. If my charge distribution is changing with time, it's like my charge is moving. It's like I'm creating some electric field according to classical electrodynamics. An example. Transition from, I noted it well now. So from 1, 0 to 0, 0, I have something like this. I have a blob, then I have positive and negative separated, and then blob again, and then separated in the other way, and then blob again. So it's like electric charge moving up and down. Okay? So, and it's actually going to be moving sinusoidally up and down. Now tell me, according to this equation here, they're looking along X. Actually, no, you can do this on your own. Circular example is more interesting. We're going to use this equation here, the one that I showed at the beginning. I'm going to ask you to trust now, but you can verify this yourself, and we'll verify together for the case of other transitions that this oscillating charge looked along, when we observe the radiation along X and Y, it's polarized like this, polarized parallel to the oscillating direction. And it's kind of easy to see because this is along K, or EZ if you prefer. And then if A is along Z and N is in X epsilon, all this is 0 and only this 0. Very easy to see. So don't worry about it. So we just see this oscillating up and down, and we see linear polarization. Neat. So stop transition from 0 to 1 to 0, 0 emits most of it. I mean, okay, forget this most. And along X and Y, it emits radiation polarized like this. Along Z, it doesn't emit at all. Okay. Now, classical way for us to explain that it cannot emit a photon along Z because angular momentum has to be conserved. Here, change in angular momentum along Z is 0. But photon carries some, so I cannot emit it. I cannot create it out of it. Now, let's have a look at this one. This one is a little bit more interesting to apply this formula. Now, it turns out that if I have from 1, 1, or from 1, -1 to 0, 0, it's like a rotating dipole. Plus charge is here, and minus is rotating. Let's now write this in XY plane, this circular motion, and tell me how electric field looks. Set a timer for 2 minutes. Very similar to what we had before. Let's say we're looking along X, right A, circular motion, vector A change. try in my mind to write. A is in XY. On Z-axis, electric field is always follows A, and it's just circling around. Explains us why along Z we see circular. Now let's see what happens along X. But you have a hunch at least. I have this rotating dipole, direction of X, X, my electric field area. A hunch. L is along X-axis. I'm the electron. Okay. Exactly. Exactly right. Let me see if I have the derivation. I do. I write my A as like this. Right? This is circular motion in XY plane. And is along I. This IJK is very Slavic way of YZ. But the habits die hard. When I do that, this and this is going to cancel. I'm going to get electric field sinusoidally oscillating. Sinusoidally oscillating electric field is exactly harmonic plane wave, highly polarized. Cool. So now we kinda, okay, this is another question for you to think about. If anybody can convince us that the linear components that are a result of this circular motion should be 2 times weaker than the other linear component. Think about it in the back of your head. But what I want us to know is to let's understand this picture now. So now when I'm looking along X or along Y, what I see is I see one linear polarizer emitting this positively polarized pi component and 2 circular ones that are oscillating horizontally. So they're emitting these 2 negative components. Another way for us to understand Zeeman effect, right? And I don't care that one is oscillating like this, the other one like this. Only thing I care is that they are in this plane because that's what determines my polarization. I don't see phases. I don't see pluses and minuses. I only see the square of the amplitude. Okay? This is the Zeeman effect. And the thing is that I need the magnetic field to split them to see this signature here. But now we understand this signature a little bit better. This signature is because of a circular oscillator. This is because of linear oscillator. Here, I don't see linear oscillator. I only see circular oscillators, but I see them as circular, hence Stokes V. And now you can think about this either as absorption or emission. If I have absorption, same thing is going to happen. We have Zeeman effect in solar prominences if magnetic field is strong enough, right? And they're basically emitting. But we also have it in the photosphere where we have the absorption. Same thing. Right. And also, of course, when I'm looking under some other viewing direction, what I'm going to see is some elliptical polarization, and I'll see contribution of all these things. This is what we see. We see two opposite circular polarization sources when we look along Z, and two negative linear polarization sources and one positive polarization source when we look perpendicular to the Z. I said here absorb, either absorb. Now, without further ado, if we combine this with what we learned about uneven population of the Zeeman sublevels, what we get. Now they are overlapping because there is no magnetic field, but because there is more, this one and this one are more populated than this one. The linear emission there, which is negative, is stronger than the one which is positive, which is pi. Sorry for this, this should be pi. When I add them all together, I don't get zero, but I get some negative. Okay? The way you can think about it, that the sublevels that correspond to the rotating dipoles, which I see as negative linear polarization, are more populated than the sublevel which corresponds to the linear dipole, corresponds to the positive polarization. Depending on how I illuminate my atoms, the different Zeeman sublevels are going to be more or less populated. And then looking from different directions, we only understand, I mean, we can kind of project the way we want, but now we're only talking basically about 90 degree scattering. We only understand what is happening there. All right. This is like the show, not the proof. There are no proofs here. That's the show that the amount of the linear polarization is intimately related to the population imbalances due. They call in these papers that I'm going to give you anisotropic radiation function. The story. In this case, photons travel along Z. They're only exciting delta M1 and delta M-1 transitions. This results in the overpopulation of these sublevels, what we call atomic polarization. Looking along Z, sorry, not Z, this should be X. The sublevels emit negative linear polarization, and the remaining one emits positive linear polarization. When I add that all together, I get net negative. Wonderful. A different way to think about this is that we can formulate emission coefficient for Stokes Q that, instead of having the level population there, has this hard-coded population imbalance in there, right? This 2 factor here accounts for the fact that my emission from this transition, sorry, this should be 1 minus 1, my bad. No, this should be minus 1 because rho has different meaning. I'm going to tell you in a second what rho is. But for the moment, rho numbers are populations of my 3 sublevels up there, right? So I have population of my pi sublevel, let's call it that way, although pi are transitions, m equals 0 sublevel, minus population of my m equals 1 sublevel, plus population of my m equals minus 1 sublevel divided by 2. And this 2 here is to account for the fact that emission from this one is 2 times stronger than these ones here. Okay? Why is this 3 here? I don't know. But in principle, I don't know. There is some. This is how we will formulate emission coefficient for Stokes Q. These are all the same. It's 0, no Stokes Q. Now what I'm going to tell you, we're not going to show that. I don't know how to show it. This thing here can be represented through some other quantity called Q0, rho02, which is proportional to the J02 that we have been talking about all along. So this thing here is proportional to the anisotropy of the radiation field. These rows here are something called density matrix elements. Density matrix elements are density matrix is a quantity that describes fully your state of your level, and in this case, where you have 3 sublevels, your density matrix should be 3 times 3. And in principle, it tells you how populated are your sublevels on the diagonal, while the off-diagonal elements would tell you how coherent these sublevels are. Now you might ask, what are the coherences and so on and so on? Well, coherences are like combination of states. And the reason why we need them is that, want to describe all the possible polarizations that we are getting, we cannot simply consider only these transitions. We have to consider combination of states and so on and so on. It's a long story that I don't know, but we can look at it together. And in principle, these off-diagonal elements of this density matrix can create your non-zero U, right? Or even non-zero V. So this is a big difference from with respect to the continuum case, is that scattering processes can in principle create circular. Exotic, it's something called alignment to orientation transfer, or vice versa, but we are not going to go there. We can read papers with that. And this brings us to final chapter, which we might not have time to finish today. We will, it's fine. Hanle effect. What is Hanle effect? Hanle effect is further modification of all these things because of the presence of a weak magnetic field. And for me, it's easier to show you in a classical way what Hanle effect would do. Full explanation requires to calculate these density matrices for both levels in general, and then see how magnetic field changes all this. Hanle effect is amazing thing. Actually, if you start reading about it, like a history and so on, it's very obscure effect, but it already is known for conference about Hanle effect. It was discovered by this guy, Wilhelm Hanle, at University of Göttingen, where MTS is now. And what he did was he did experiments with mercury vapor. Ignited mercury vapor from one direction, mercury vapor scatters the light is polarized, then he put magnetic field into that vapor. The rotation, there was a rotation of the plane of polarization of that and decrease of the polarization. That's what phenomenologically Hanle effect is. Rotation and decrease in the polarization, presence of the magnetic field. It led to the confirmation, basically, that there is such thing as coherent superposition of two states. For us means when the photons are scattering, I don't have to excite it to one of these specific eigenstates. I can excite it to a combination. Crazy stuff. The reason, for me, the easiest way to understand this, because of course I don't understand this fully, I'm like parroting something that I heard and interpreting it on the go. But the easiest way to make peace with this is to say magnetic field is the big boss in quantum mechanics. So even though my radiation field is axially symmetric along z-axis, if I put magnetic field which is oriented horizontally, magnetic field becomes my reference direction. Now my radiation field is not axially symmetric anymore, and things become crazy again, right? And one of the important consequences of this, which should be aware, is that our symmetry of the radiation field coincides with B. So if our B is vertical, Hanle effect will not act. And tomorrow when we play with Hazel, we're going to see that that's really true. Main component, the main change here is that magnetic field is going to become our new quantization X, which means, and the way to understand this is to say, well, there are these things that are oscillating and rotating, and I put them in the magnetic field, and then that magnetic field exerts some Lorentz force on my electron, and the presence of that Lorentz force modifies or doesn't modify the plane of oscillation of my electron and does something, right? I'm going to convince you now that if magnetic field is really along the z-axis, my electron is rotating like this, the force is going to be pointing like this. And because this force is pretty small, because magnetic field is very weak, nothing changes, right? The plane of the rotation doesn't change, right? I'm just squeezing my circle or stretching it out. I'm not changing, I cannot change the plane this way. But if I make it like this, if I make magnetic field pointing here, and this is the rotation, different points, I'm going to have different force acting. This is going to cause precession of my plane. Eventually, I also have another components of the velocity will modify. This will cause the precession. This is like from quantum mechanics when we were talking about precession. The spin is like this because I'm rotating like this, but then I introduce some magnetic field that causes the precession of the spin, right? For us, what it means precession of this axis here, precession of the plane of the rotation. Precession of the plane of the rotation means that, according to what we said before, that now my electric field is not only oscillating for an observer from the outside, it's not only oscillating like this, okay? It's oscillating along more than one direction, okay? Which explains the decrease in polarization, okay? That's I didn't make the slide for that. So imagine that my phone is linear projection of a circular thingy on you. Before it was only oscillating like this, but now it's oscillating like this. You still see it as a linear polarizer, but that linear polarizer is oriented like this or like this. Cool. So if it goes from like this to a little bit like this, little bit like this, little bit like this, it means that it's still linearly polarized, predominantly horizontally, but less. Precession is huge, and if it's doing this, then there is no polarization anymore. It's completely destroyed. It's what we call saturated Hanle effect, and it will completely destroy the polarization for us. Similar thing happens with the other oscillator due to the interaction between the magnetic field. However, doesn't explain us one thing. There is no rotation of the polarization plane, right? Everything is still symmetric with respect to you. Now you need to trust me a little bit. What's going to happen here? Okay, we're going to go back to this. What happen here is that things don't emit like infinitely rotating circles, like infinitely rotating dipoles. They are decaying. Their amplitude is decreasing with time. It's like electron is falling down. What does it mean falling down? It means it's exciting through time, right? It's going toward the unexcited state where it's like just one block, right? The amplitude of my rotating dipole is decreasing, and it's precessing. Now means that what I'm actually gonna get is something like this. This is rotated by 90 degrees, so bear with me, but it means that what I'm gonna see is, instead of just seeing one rotation direction, I'm gonna see a little bit of uneven rotation here, right? And now what you can see, if you imagine a little bit, is that these different projections are gonna have different lengths. So what I'm gonna have here is I'm gonna have non-zero Q and non-zero U. This plane here if the amplitude wasn't decaying, I wouldn't have that. If the precession is so fast that the amplitude doesn't have time to decay during many precessions, I'm not going to get any Stokes U, sorry, and also not any Stokes Q. Principally, if I have weakish magnetic field, it's going to make things completely asymmetric for me, and it's going to give me both Stokes Q and non-zero Stokes Q. That's why it's called Hanle rotation. Sorry about that. I want to go back here. What strong magnetic field means, it means how does the strength of the magnetic field, how does this so-called Larmor frequency, which describes how quickly this precession is happening, how much it compares with your Einstein coefficient of the spontaneous emission. What is the classical interpretation of the Einstein coefficient for spontaneous emission? How do we call it in classical terms? Lifetime? Okay, it's also quantum, more classical. Rhymes with, okay, it rhymes with dancing. Damping, right? Einstein coefficient is actually your damping, or damping of your classical oscillator, right? So the more damped that is, the faster this is going to decay, the less magnetic field is going to matter. And this is why we say that Hanle effect is great for various strengths of magnetic field. because we have spectral lines with a range of Einstein coefficients. We have 10 to the minus 8, 2 times 10 to the minus 8 is transium. That's why it's a photospheric line that exhibits the Hanle effect even in the photosphere. Then you have 2 to the 6, 2 to the 5. Right. Good. So this is a quantity that appears very often. I'm going to ask you probably tomorrow to calculate critical Hanle field for helium atom. So try to remember this. This is lambda factor here, which for Zeeman triplet is 1, but it can be different than 1. Okay. Good. So this is what we saw, and this is like different cases. If your Larmor precession is small, you get a bit of the rotation. If your Larmor precession is larger, you get quite some rotation. If your Larmor precession is very large, which means if your magnetic field is very strong, you will get a lot of precession. You will wipe out all the linear polarization, both in Q and U. Go ahead. It's only in this. Yeah, very good question. It's only in this specific configuration that it diminishes. But at some point, magnetic field is going to be large enough that this doesn't tilt it, and the change in Stokes profiles, they're both 0. You're not. Yeah. You're not. We're going to list that later as disadvantages. Is that once you reach something, you're not sensitive anymore. And if it's not pointing directly toward you, you are still sensitive to the direction, but not to the strand. And you'll see it tomorrow when we're on case. Go ahead, Marcel. Fine. A. Yes. They depend on A. Yeah. A is, you can call it inverse lifetime of the upper level. You can call it Einstein coefficient of spontaneous emission. You can call it damping, radiative damping coefficient. You can call it anyway. So now how to put Hanle effect formally in your equations. Let's say you accepted all what I taught you before, and you're now like, okay, I want to add Hanle effect to that. Well, Hanle effect is going to do few. Well, first of all, it's going to look very simple. I can just say Hanle effect modifies my scattering matrix by adding this coefficient here. Okay. What is this? Well, this is 1 over 1 plus I times something. What does this do? Well, this will, because I will integrate over something times this will decrease my source function for polarized radiation. Won't do it for unpolarized because there is Q here, and for unpolarized source function Q is 0, so Hanle effect doesn't matter. It also change the phases. It will make some things. It will change the balance between, real and imaginary part of my source terms in formalism here. However, there is one thing that is not shown here. Matrix now, when there is magnetic field, has to be, there is no Z anymore. Z now has to be oriented along B. My B is not a vector here. Why am I only playing with the amplitude of the magnetic field? Because I have to formulate all these quantities along my B axis. Now, even though my radiation field was axisymmetric along Z, if I put B, which is not there, which is not coinciding with Z, like my radiation field is not isotropic anymore, right? It's not axially symmetric anymore. It's very important. This looks like I'm only adding this, but I'm also rotating the reference system. I need to change the angular distribution of my incoming radiation from what was prescribed along new axis, which make things a bit complicated, right? So, one question which is more philosophical, I think we have time for that, is, well, H is equal 0, there is no this, but I'm still oriented along magnetic field. Why? How come? Will I get different emergent polarization than in non-magnetic field case or no? So if H is 0 or very, very small, but still, even if it's very small, I need to calculate these things in new coordinate system, right? Will my emergent polarization, when I put all this back in our formalism, will it be different than when Z was my referent axis or not? Try to calculate. Oh. And this coordinate system, this orientation for theta and theta prime any way I want, made it oriented along Z just because it was easy for us to calculate the quantities, because everything was axis symmetric with respect to Z. But I can orient it anyway. These two things here are going to look much more ugly, much more components are going to be non-zero, but I need to get the same final result. Another thing is that if Q is equal 0, right, there is no Hanle effect. This is what I was saying. If H is equal 0, Hanle effect disappears. We have this, but oriented over different axes, but still amount to the same result. It's not a problem. And Q is equal 0, right? I have equal 0, then where does it matter? It matters in J00, which we don't care about, and in J02, which we care about, but yeah. So it means that I'm now I'm defining my J02 with respect to the magnetic field, right? So that part of the anisotropy of the radiation field with respect to the magnetic field is immune. That's the point. Maybe not so important right now because we are almost at the end. Okay, this was perfect, but this kind of allows us to understand these things here better. Now, when we have Hanle effect, because there was one weird thing here. If you have time to look at this plot, it was on the title. But this is, let's focus on the top one here. Looked at it. I saw it. Okay, I have a level. I don't care about. It has a lot of electrons there. And I have these 3 upper levels. Radiation is coming from below. Here is overpopulated. How? Once again, before I told you, radiation is coming here. Overpopulated. Yet here, this one here is overpopulated. Javier make a mistake in this plot? In this sketch? Or is there something else? There's a magnetic field which is like this, right? Even though this is our atmospheric normal and we are looking from here, because magnetic field is pointing along this direction, this has to be my Z. Everything rotates. And now this one is going to become more popular. Very good. There is a lot to unpack in this thing. Similar thing is here, right? Here you have the so-called selective absorption. This one is more absorbed because this one is perpendicular, right? And if both are split, I need to look at all the combinations. Right. There are also additional effects that can influence the line polarization. I'm not going to talk about them. I'm going to leave them for Friday, so we can skip this. And there are a few more things that are tricky here, which is because Hanle effect exhibits few more ambiguities compared to your good old Zeeman effect. For Zeeman effect, we only had one ambiguity, phi and pi plus phi, right? You cannot tell between these two magnetic fields with Zeeman effect. Here, there are more combinations. And even for simple Zeeman effect, for simple Zeeman triplet, you can express Q and U through these equations here, and you can look for different combinations of these angles to see ambiguity. I'm not going to talk about this. Instead, tomorrow when we fire up Hazel, we're going to just see them when we try to invert stuff. We'll see confusing, completely different results that produce identical Stokes profiles. Anyway, helium-10-830 is not Zeeman triplet. It has 3 components, so we cannot do that. Yeah. So the only thing that I want you to remember before we play with our little code tomorrow is that I like to say that there are 3 regimes of line polarization. Simplest one is just scattering. Did I break this? Just scattering. I only get Stokes U. Simple case. I have Zeeman effect. I have Hanle effect with the big magnetic field. Sum of Q goes to U. Polarization plane. And if I really do hard, if I give strong magnetic field, then I have different splittings. Then I have Q, U. So on Friday, we're going to talk about many different things. We're going to finish with this because we're going to be tired. I'm just going to present you some papers and tell you some stories. We're going to see what is the second source spectrum. What is the non-LTE problem of the second kind? What are the turbulent magnetic fields? How do we put all this in the context of radiative transfer? Why is multidimensional radiative transfer important? And so on and so on. None of you fell asleep, so I can skip this and we can go to dinner and to. So if you have any questions, I'm here. Just ask. If not, you can ask there and so on and so on. Tomorrow we start straight with, I will just introduce you with a few slides in Hazel, and we're going to start coding immediately after that. Any questions before we split? Okay. Or to initiate. At the end of the day, you're all tired. It's better if you don't sit. If we maybe step outside for half an hour before the dinner's up.
Outside like we do for lunches. And that starts at 4:30. And because of our regulations, there's no alcohol. So I'm sorry, this is not really a real banquet. It's a NCAR style